working in this field can and will destroy your career. Being interested will cause difficulty in your personal life. Yesterday we talked about all kinds of things. At a high level, we're trying to figure out what the Fleisch-Ponz experiment is all about. What it's trying to do. I presented a series of arguments moving in the direction of trying to make sense of it. The arguments that I'm making are my point of view. I don't believe it's the case that my ideas are uniformly accepted within the shrinking cold fusion communities. But in order to understand things, we need to put on our electrochemical hats and understand something about the basic electrochemical reactions. Wilmer brings deuterium to the cathode. Deuterium leaves via the gas formation or tackle reaction. And we're trying to understand a little bit. We adopted an ansatz that perhaps what's going on is D2 formation. And in order to understand D2 formation in palladium deuteride, we needed to understand something about embedded atom models for hydrogen and helium, which allowed us to begin to get intuition about what was going on. What we found was helium had a higher energy depending on what the background electron density was. Hydrogen is sort of the same thing, except at low electron density there's a preferred electron density that likes to see. You can actually seem to understand molecular HD based on that simple notion alone. We can also understand why hydrogen or deuterium goes into the octahedral site in palladium. We can also understand why nickel has lower solubility than those ideas. However, pursuing the ideas further, we find that D2 is not going to form in bulk palladium deuteride because the electron is too high basically everywhere. And having electrons be high causes bonding of the or occupation anti-bonding states that pushes the deuterons apart. On the other hand, if we introduce a vacancy, we can lower the electron density. And from my perspective, that's kind of the key to what the Fleisch-Ponz experiment as an exercise in physical chemistry is all about. And I talked a little bit at the end in a rushed fashion. I'm going to come back and go more slowly over that today. So the idea is that D2 formation is at least possible near an O site, near monovacancy. And I'm most interested in monovacancies, but the arguments would apply to more complicated vacancies as well. It turns out in the literature, we've got an analog to the proposed state. And the analog is a sigma-bonded molecular H2 state that's been observed experimentally and been calculated theoretically on the surface of palladium hydride on the 210 surface. The binding energy we found was 270 millivolts, which from my perspective is a fantastic number, and is a number which is consistent with the energy, I think, of a sigma-bonded dihydrogen D2 state. So we proposed that excess power in the Fleisch-Ponz experiment was connected to D2 occupation. So the idea is that in the experiments, there's during an experiment in the on the Fleisch-Ponz experiment in lithium deuteroxide type electrochemical version experiment, excess heat isn't seen at low loading, but above 0.84 going on, excess heat is observed. So the proposal is that if we're making D2 in vacancies, well, D2 is unstable at low loading because if the other octahedral sites around one vacancy are not occupied, then the D2 is happy to fall apart and occupy the unoccupied octahedral sites. So if you do some physical chemistry and calculate what's the D2 occupation's function of loading, assuming state energy in the neighborhood of 270 millivolts, then you basically reproduce with a D2 occupation curve the XSC as a function of loading curve, which suggests that, well, it suggests consistency. It doesn't prove that's what's going on. We need better diagnostics, better experiments to clarify unambiguously what's going on in the experiment. But we have at least consistency. We started to argue about vacancies being stabilized. And that was in response to the question which resulted in flying through a very large number of view graphs and a large number of points in a very short time. And I thought maybe I should start there and do it a little bit more slowly. So based on the discussion at the end of last time, the argument then is we need a vacancy to get a D2 molecule in a palladium deuteride system. Palladium contains vacancies. There are vacancies in palladium. There's not very many vacancies. As Mitchell described in some experiments that we tried at the high voltage center here at MIT, we can bombard palladium and make vacancies. In the case that we did, we bombarded palladium and nickel with electrons, made a lot of vacancies, and watched them go away. They anneal. If you make a lot of vacancies with electron beam bombardment, at least in the case of palladium, they anneal back to the saturation density, which is between 0.1 and 0.2%. In metallurgy, that's a huge number of vacancies. From my perspective, from the cold fusion business, that's nowhere near enough vacancies even to begin to be interested in. So saturation fraction of vacancies, from my perspective, is not interesting. There's a more subtle approach. And the more subtle approach is to notice that vacancies are stabilized with the addition of hydrogen or deuterium to the lattice. So the reason that there are so few vacancies in the first place is that it takes energy to make a vacancy. And it takes a lot of energy. It's on the order of electron volt. You stabilize vacancies by roughly 0.2 electron volts. The 1 electron volt might be a little bit more than 1 electron volt, but 0.2 might be a little bit less. So by the time you get 5 or 6 around it, hopefully 6 rather than 5, then you've stabilized enough to basically balance out the 1 electron volt formation energy. So under those conditions, if you get high enough loading, you can stabilize the vacancies, and the vacancy phase version of the system is thermodynamically preferred.
Yeah, just for understanding, does the stabilization occur? Does the hydrogen atom then take the place of a palladium atom in the lattice, or is it does it go in between? As it is to go.
As we saw yesterday, the hydrogen and deuterium has a certain electron density it likes. Now, at the site of the vacancy, that's where the palladium's missing. The electron density is very low. And if you like, the hydrogen wants to see a higher electron density. So if you put a hydrogen at the vacancy point, it's going to look around and say, higher electron density over here. It's going to wander off until it finds its preferred electron density, which happens to be very close to the octahedral site. Good question. Good question. So back in the mid-90s, I'm sorry.
The impurities we've talked about in the metal palladium, would that also create these vacancies because of, it's not the same?
There are certainly impurities in the palladium, as we remarked on yesterday, that having basically higher levels of impurity. 5-9 palladium is very brittle and breaks at the yields. The yield strength of the metal is 400 to 500 megapascals, and you load it high enough to reach that as an internal pressure, it just breaks. So you need the impurities. I'm not looking at the impurities as being the source of vacancies. Impurities are certainly defects, and the local situation is a little bit different around an impurity. From my perspective, in terms of the hydrogen, if you've got another metal atom sitting where the palladium should be, and it happens not to be palladium, So you can have minor changes in the electron density, but in the octahedral site, the changes are sort of going to be minimal. If the electron density happens to be lower, then the hydrogen will want to be there, and if the electron density is higher, then it won't want to be there. Otherwise, not a big deal. Okay, so about in the mid 90s, I was very interested in this, and I took the available thermodynamic data for stabilization of vacancies, and I went and I calculated it out to see what it would mean in terms of how many vacancies at what temperature, at what loading. And I calculated this for palladium hydride and this for nickel hydride from the existing data. Since that time, more experiments have been done, there's better models, and I very much need to update this curve. But the conclusion is that if we load palladium up to 0.95, and if we operate near room temperature, that what we find is that the fraction of vacancies we would expect would be 25% in this model. And 25% is sort of the maximum number of vacancies you can get in an ordered phase called the Fukui phase, which I mentioned last time, and I'll talk more about this time. Nickel hydride works the same way. Hydrogen loading stabilizes the vacancies. The only thing is that in the case of nickel, the stabilization is, if you like, more effective, so you'll need to be at a loading of 0.65 or thereabouts in order to stabilize vacancies in nickel. This will be much more important to us on Friday, but since we're interested sort of systematically in metal hydrides and vacancies at the moment, having them both be on the graph here is useful. Now the 0.95 number here is interesting to me because that suggests that if I go back to the SRI data, which segregated experiments which worked versus experiments that didn't work as a function of peak loading during the course of the experiment, then we see here's 0.94, 0.96. So these are all positive results. Red is at SRI, green is at NEF Viscotti. And back here are the Caltech and MIT negative results. The peak loading was nowhere near close enough to, or high enough to do anybody any good. So here the question is why should the loading need to have reached 0.95 somewhere during the course of the electrolysis? Well, if we think we need vacancies to make D2, and if we think that at a loading of 0.95 we stabilize the vacancies, maybe we have the beginning of a physical basis for a requirement for a loading of 0.95 to have been reached. And again, it's a conjecture. It's interesting. It's not been proven for the Fleisch and Pons experiment, but I'm going to present some indirect arguments. In the process, you go back. If you can stabilize the vacancies just by putting hydrogen into the lattice, well, that's interesting and it's fun. And Fukui, very famous Japanese metal and hydrogen and metals researcher, was looking at the same kind of thermodynamics. And the difference between me and him is that he happened to have a diamond anvil press and could load nickel and palladium up to very high loading and very high pressure. And so he did it. If you start with palladium hydride, so again, FCC structure, chessboard on the bottom, shift to chessboard here, another chessboard on top. Well, here's what happened in Fukai's experiment. So if you like, this one, 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 there's a lot of palladium missing. And what Fukui found is that 1 out of every 4 palladium atoms, by the time he was done with this high temperature, high pressure, high loading processing, that he had vacancies produced for 1 out of every 4 palladium sites. From my perspective, this is really, really interesting. In a sense, what Fukui makes, I think, is exactly what we want. I mean, if you want to make molecular D2 in palladium deuteride, you don't want to work with this because the electron's too high everywhere for D2 to form. But if you got this, then you have electron density low enough that you can have D2 formation.
if you have so many vacancies, would you notice that on the volume of your?
The volume shrinks a little bit. If you like, we notice that addition of hydrogen stretched out the lattice, made the volume be bigger. Well, you take hydrogen, you take palladium out, and the lattice shrinks a little bit. It's a little bit smaller lattice and smaller lattice constant.
With the palladium, I mean, when you create a vacancy, it doesn't just boil off, does it?
Well,
It settles on the
in
outside.
Fukai's experiment, you've made conditions under which the vacancies are thermodynamically preferred, but in Fukai's experiment, he's raised the temperature very high, so the palladium atoms can move around. The palladium atoms are rearranging and going to the nearby surfaces and making the thing bigger.
So that effectively you have a volume gain,
Well,
because you've got a less dense structure. If you,
yeah, I think that's right. I think that's right. You have more lattice sites. The lattice constant's a little bit smaller. Okay, so if we think about diffusion of vacancy cluster, that's been studied. Namely, we're imagining that in a cold fusion experiment, Fleisch and Ponsel, we reach a loading of 0.95. We reach the magical physical chemistry regime where the vacancies become stabilized. We'd like to see our whole lattice turn into Fukai phase if possible. Now the headache is that at room temperature, the atomic self-diffusion is pretty slow. This has been studied. So Fukai and colleagues studied vacancy diffusion and discovered by a standard diffusion law with a barrier energy which is about 1.2 volts. 1.2 volts in connection with diffusion isn't the world's fastest in this particular case. Characteristic diffusion in a time scale in the order of 10 to the 6 seconds is 0.15 angstrom, which leads us to the conclusion that if we do achieve a loading of 0.95, a heroic loading of 0.95 in the lattice, keeping in mind that we notice that getting high loading is problematic because the chemical potential of deuterium is shooting up. It becomes exponentially more difficult to get high loading. But if we do, we reach 0.95 loading, we want to turn our whole cathode into Fukai phase. We're facing this, which basically says the vacancies can't move in a time scale relevant to the experiment at near room temperature. So we don't do any good. So loading to 0.95 at the moment, which could make the Fukai phase, isn't going to make the Fukai phase. So we're looking at this, so much promise in the approach, and we're shot down. It doesn't work. So this draws our attention to Spock's co-deposition experiment, and again I draw attention that Mitchell back in 1989 was smart enough to understand that co-deposition can make a difference. He also pioneered co-deposition as well. So basic ideas, you do your electrochemistry, you put in palladium chloride into your electrolyte. Chlorine chemistry, my understanding from my electrochemist friends, is not very much fun. There's odors, there's toxicity, and then there's chlorine chemistry, which can confuse the excess heat measurements. However, we remarked on Monday that in the case of Fleisch and Pons experiments and at the replications at SRI, you had to wait 3 weeks, a month, 6 weeks. You had to load, be gentle with your cathode, eventually raise the current, exercise your cathode. And it took something in the neighborhood of a month before you could see any excess heat. Well, here's Spock's experiment. Here's time in minutes, here's 0, here's 60, and here's the temperature shooting up following co-deposition of palladium. So in the Spock experiment, excess heat turns on very quickly. We noted that the diffusion of hydrogen deuterium into the cathode occurs in a relatively short time compared to the month. So the question is, what's going on during that time? I'm looking at this and thinking, well, co-deposition palladium at high loading, if the thermodynamic arguments are right, then the co-deposition should be forming high vacancy Fukai phase palladium. So the co-deposition at high loading should be making what it is, the environment that we need to see molecular deuterium. So we like palladium vacancies so it can host the molecules. Deuterium and hydrogen stabilizes the vacancies at high loading, but the vacancies don't move. So if you like, we can make them anew if we achieve high loading and make new palladium. If we co-deposit palladium onto the surface, then by the thermodynamics of vacancy stabilization, we'll be making a high vacancy concentration in the co-deposit regime. So maybe this is an explanation for the SRI curve, that if a cathode reaches a loading of 0.95, if there's some inadvertent palladium co-deposition, you get some vacancies, and you can do your business. I had mentioned that last time when I was zipping through all this stuff, the Let's experiment. So Let's, Cravens, and others had tried the Schwach co-deposition protocol. Now, Schwach didn't publish his protocol, but at Speyworth, where the work was done, Pam Boss had been publishing a version of the Schwach protocol, which involved running at very low current density. So she would run at low current density in order to have the palladium adhere to the cathode surface. And if you crank the current density up under those conditions, then the palladium deposits much faster, and it doesn't deposit very well. It falls off and collects at the bottom. So Let's tried the Pam Boss's protocol for co-deposition, looked for excess heat, didn't see anything. Dead as a doornail, goose egg. So then Let's was familiar with some of my arguments and my ideas, so I said, well, obviously what's wrong is you've not got high enough loading at the surface when your current density is low. So he said, let's crank up the current density. So he boosted the current density well over 100 milliamps per square centimeter, started co-depositing. The palladium came out, co-deposited like mad, didn't stick very well, fell to the bottom of his test tube. He scratched his head and said, that's no good. So then he said, well, what do you have to do to get it to adhere? And what he said is, well, let's co-deposit more slowly, so you reduce the concentration of palladium in the electrolyte by 25 or so, and co-deposit high current density. And as soon as he did that, he saw data something like this. So you co-deposit the, in this case, titanium, which I think the titanium was a separate. Co-deposited on a copper cathode coated with gold. Palladium co-deposition occurred, excess heat turns on promptly. Here he replaces the heavy water with light water, and the excess heat goes away. But if you like, this shows that the excess heat, it supports the notion, namely co-deposit palladium high current density, make the vacancies, excess heat, short time, don't have to wait a month, 6 weeks, and there you have it. Now, it's important in this field to get confirmations of the approach. And I think NRL tried Letz's protocol, didn't see anything whatsoever. I think Rick Cantrell at Coalescence tried the protocol, didn't see anything. Mel Miles tried Letz's protocol and saw the biggest excess heat event for co-deposition that he had seen in ages. He was very pleased with Letz's protocol. So we have confirmations in Letz's lab, and we have confirmation by Mel Miles.
Who didn't see, Coalescence didn't see it? Who else didn't see it?
NRL. Okay, so over the years, I've been thinking about how do you quantify the vacancies? How do you know that you've made the vacancies? And I've been struggling with this for a while. And a number of, I've been aware of thermal desorption. And last time I flew through this, I was all excited about it. In this experiment, this is done by Fukai. And Fukai made Fukai phase nickel hydrogen using the high pressure, high temperature protocol described previously. So this is Fukai phase missing every fourth nickel instead of palladium. So when he heats it up, the hydrogen comes out. So what you do is you scan the temperature. You start out in your room temperature, and you warm it up, and then hydrogen starts to come out. And you warm it up, and then hydrogen that was hiding in deeper traps comes out. And then you warm it up more, and then hydrogen in even deeper traps comes out. So you can do some spectroscopy. The first peak is identified as being due to standard bulk octahedral hydrogen. So it comes out at the lowest temperature. And then he sees two peaks associated with the vacancies, 640 C and 800 C. So then, at issue is that can you make vacancies in co-deposited nickel? So he found, so Fukai was interested in the issue of stability of the vacancies. If you make Fukai phase material, you make these vacancies. Do they stick around? And so he got 32-year-old electrodeposited nickel in this case and did a thermal desorption scan on it. There's no 400-degree C signal, basically, because it's been sitting around and all the hydrogen is gone. But the traps can retain some hydrogen, and when he heated them up, he saw emission at 624, which is sort of like the 640, and he saw at 763, which is like 800. So this argues for thermal desorption being a diagnostic for vacancies. So if you like, we have a tool now. Suppose you can imagine doing Schwack co-deposition or doing co-deposition under Pambassa's protocol, say for example on copper, and then doing thermal desorption afterwards. Now if it's true that there's no vacancies being created because the current density is not high enough and the surface loading is not high enough, then you should see the palladium analog of this peak and not the palladium analog of either of these peaks. On the other hand, if you crank up the current density, if you really got high loading and you've stabilized the vacancies and you co-deposit under conditions where you stabilize the vacancy, you should be making lots of them. You should be making Fukai phase material, which means if you do thermal desorption, you should get peaks like this shown up. Now, also the case is that if you only make a few vacancies, these peaks will show up, but they'll be small. If you make a lot of vacancies, these peaks will show up and be much larger. So you have the possibility now of having a diagnostic that will be able to actually prove that you've made the vacancies through this method. So far, no such diagnostic has been implemented. So
Would X-ray diffraction work?
X-ray diffraction will also work. It's not as easy because you have to do X-ray diffraction on a very small. If you do it on copper, then you do palladium on copper, then you don't have any interference, so you can actually look at the palladium. If you do palladium on palladium, then it's much harder to do. So the proposal here, going back to Fleischmann and Pond's experiment, is basically the following. So at SRI in Fleischmann-Pond's lab, they load for an awful long time. So in the case of SRI, there's just a platinum anode and palladium cathode. So you do your electrochemistry, you load, but at SRI sometimes they would do protocols where they'd run cathodically to load and then anodically to deload and then cathodically to load again. And an anodic cycle to strip the deuterium out would also cause the palladium cathode to corrode. It wouldn't be cathodically protected anymore, which would get you some palladium into the electrolyte. So if the palladium's in the electrolyte, then if you run at higher current density, if you manage to get the palladium to stay in the electrolyte, then you can have inadvertent co-deposition. And the inadvertent co-deposition happens at 0.95, then by accident, you're making the vacancies. So this is the situation in SRI. Turns out in Fleischmann-Pond's experiment, I drew attention on Monday to a palladium reference electrode. Fleischmann-Pond's were the only ones getting positive results to do that. Caltech was the only other group to run with a palladium reference electrode, and they didn't see anything. But if you have a palladium reference electrode, you got your cathode, you got your anode wrapped around, you got another palladium electrode sitting there. But if it's a reference electrode, it's not cathodically biased, which means it's not cathodically protected, which means it's going to be dissolving slowly. And if it's dissolving slowly, it's giving you a constant supply of palladium for your electrolyte. So in the Fleischmann-Pond's experiment, their experiments were different than everybody else's experiments in the field, because they had a source of slow palladium into their electrolyte, So when they achieved high loading, they could co-deposit, they can make their vacancies, and off you go. So I'm of the opinion that that is a critical part of the Fleisch and Pons experiment. I think that the reason that they got such excellent results is because they had a palladium reference electrode. An elemental surface analysis of the surface of the palladium cathodes in Fleisch and Pons experiment was carried out many times. Here's one reference for it. But platinum, copper, and other impurities are seen at depths greater than 1,000 angstroms. You might say, well, why should that happen? And the why should that happen is that platinum as a noble metal is an anode, which isn't supposed to be attacked because it's noble, does get attacked some. You get some platinum coming off of the anode, and then you get co-deposition under the surface of the palladium. So you can actually see your co-deposited region because it's got some platinum in it. So the evidence on the surface analysis of platinum on the surface supports the notion that co-deposition went on in the Fleisch and Pons experiment.
Because the original cathode is pure, and that the surface has those impurities, so you can separate the original cathode from what was co-deposited.
Well, certainly the interior also has platinum and other stuff at ppm type levels, but the amount of the surface is much, much greater. So it's completely clear from this interpretation, which is not the interpretation that's made in these analytical papers. So this is my interpretation. So if I interpret it this way, then I can tell exactly what regions co-deposit just by looking at the trace of what it is that's on the surface. So the big picture then that we're evolving to in the Fleisch and Pons experiment. So what is the Fleisch and Pons experiment actually doing that's useful and helpful? So you start out with palladium, load up with deuterium, but the internal region here from the arguments I've given is inert. It doesn't do anything at all. It's just sitting there. On the other hand, you get co-deposition palladium on the surface, and if you do that when the loading is very high, it makes lots and lots of vacancies. Those vacancies can host D2 on the surface. And according to me, that's what it is that the Fleisch and Pons experiment's actually doing in terms of constructing a region where something new and something interesting has the potential of happening. In Fleisch and Pons experiments, uncontrolled, and all negative experiments didn't reach the 0.95, so you can't make the vacancies. In the positive experiments, except for the Schbach experiment LETS protocol, vacancy formation is uncontrolled. In Mitchell's electrochemical experiments, vacancy formation is uncontrolled, but on the other hand, if you make your spiral, then according to me, that gives you the chance of having the local strain energy aid in making vacancies easy to form. The takeaway message. I want palladium vacancies to host D2. Stabilize them above 0.95 in palladium, above 0.67 or something in nickel. Proposing this as the physical reason of the experimentally observed constraint that cathodes that didn't load to 0.95 didn't show anything. Superabundant vacancies are formed in Fukai's experiments, palladium, nickel, and also in other metal hydrides as well. Co-deposition is proposed to produce high vacancy concentration when it's at high loading. As a result, we can begin to understand why excess heat turns on quickly in the Schbach experiment and in the LETS experiment. So confirmation of these ideas by LETS experiment and by Bell-Miles confirmation. Proposal that the reference palladium electrode is key in the early Fleisch and Pons experiment in terms of getting a much higher level of excess heat than anybody else was getting at that time. My takeaway message slide, so it gives me a chance to take a breath and entertain questions, comments, thoughts. No thoughts. You're going to make me keep going.
For Pons replacement, we're using a palladium as an electrode also.
They used palladium as their cathode to load, and then they had a second palladium reference electrode. And the idea is to measure the loading, by measuring the voltage difference between the cathode and the reference palladium electrode.
And that was the source of the additional palladium?
According to me, I'm
According to-
arguing that
That's the
an
proposal.
unprotected palladium reference electrode would supply palladium that could be co-deposited.
So, I think I follow your argument that we could have D2 on the surface of Hans Fleischmann's experiment and these other experiments through co-deposition. Once we have D2 on the surface, though, what do you think is happening next? Because that to me is the kind of
I'm going to be spending an awful lot of time talking about that.
Okay, all right.
Yeah, I got a question about instrumentation on the palladium reference electrode. Do we know what the circuitry was that was attached to that electrode, and whether there was a small current, either positive or negative current, as a consequence of the measurement activity, or was the electrode essentially floating open circuit? Really open circuit. I'm talking down to nano.
No, I understand the question. I happen not to know the answer to that. The documentation that that exists, from what I know, is in the patent that they applied for, that's available, the 1990 patent. So we'd have to go back and stare at that. I don't remember the circuitry for the reference electrode being there. However, I wasn't paying attention to it. So that would be the reference that would.
Thank you for your help.
I would like to. I'd like to say it worked like this, but I don't remember. I don't know.
In the Fleischmann-Pons experiment, did they have excess heat turning on relatively quickly, a la the CODEP experiments by Letts, or was it more of a month-long build-up?
Oh, again, in the Fleischmann-Pons experiment, the early 1989-1990 experiments, you start out loading at low current density, very gentle for your cathode for the diffusion arguments I gave and the destruction of cathode arguments that I gave earlier. And then you bring it up and you get high loading. And then you hope that excess heat comes. Excess heat doesn't come, you turn it down, you play with it, you bring it up again, you try again. And if you don't see anything, then you try it again. So typical experiment would go on in this kind of fashion for a month or 6 weeks. So there was no sudden turn on, that Fleischmann-Pons would do something to induce it. It would happen at its own whim. Whereas in the Spock's experiment or Letz's experiment, you do the co-deposition and it turns on. It's almost like switching on a light. Not quite. It's not quite as fast as switching on a light.
Yeah, I find this very convincing. You keep saying this is your idea of what happened. How many people agree with you in the community?
I was thinking about it. I think there's a grand total of 1.5 other people that agree with some of the things that I say. I mean, for example, there are thousands of people that agree with Whittam Larson, and there are hundreds of people that agree with Ed Storm's view. I think there's 1.5 people that agree with mine. I'm not going to mention names. Other comments or questions?
Interesting. A thing that is not so simple to understand is that excess heat means that there are a lot of reactions that do almost at the same time. So there is a sort of jump. So something that is exciting such reactions. So that they do not once, but from zero, and after a certain activation, abruptly there are a large number of reactions. And so this is, let's say, not very explicable in standard.
I agree completely. And during the next day and a half, almost 2 days, we're going to be thinking about exactly that a lot.
Is D2 or D in certain condition when D2 goes into palladium?
Well, when D2 goes into palladium, in bulk palladium, the D2 breaks up into individual deuterium atoms,
Yes.
and they go to the octahedral sites.
Yes.
Now, here we're arguing that we make vacancies on the surface by co-depositing at high current density. And near the vacancy, there's low electron density. So there we can make something that looks like a D2. It's not quite D2. The separation is more than for the vacuum molecule. But from my perspective, it's D2 under conditions of reasonably high electron density,
Yes.
so it can be screening. So
Yeah.
we're going to be very interested in that shortly.
Okay.
I was just wondering if your cathode, designing your cathodes and changed all the you put forward, so you've seen as a lot of surface area would of course increase this co-deposition.
Right. I mentioned that there's like 1.5 people that buy my ideas, so there's not been any experimentation past what Lutz has been done following these ideas. And there's also almost no resources in the field now, so even if I could convince my friends to do the experiments, there's no way to get them done because there's no resources.
I have a question. Is there a way to prepare the cathode other than using electrochemistry, like by sputtering
As we talked about before, certainly sputtering could be done, but sputtering by itself wouldn't be expected to make lots of monovacancies unless you co-sputtered hydrogen or deuterium or something under conditions where it could be kept in the lattice to get the high loading in order to stabilize the vacancies. So I don't think so. On the other hand, one of my colleagues had the bright idea of working with an interesting lattice structure that had palladium in it, but also had lower electron density next to it. So as an interesting alloy structure. It was actually tested and showed some excess heat. So there's one example where that was done. That work hasn't been presented in public or published yet. So I mean, I've seen presentations of it, and I hope that it does get written up and published, but one never knows about these things.
What about the water plasma?
What about what?
And the water plasma. You said that bombardment with some particles.
Electron beam bombardment of a fully loaded palladium hydride, palladium deuteride should produce lots of vacancies, and they should be stabilized if the loading is high enough. So that would be a good way to make a lot of material with a lot of vacancies. The only thing is in my view, Lutz's co-deposition protocol is much easier. Okay, I want to talk a bit about products. So now, if you like, we finished an extended argument, and we're going to begin a new argument. And this argument is going to lead us in 2 directions. It's going to lead us in one direction of applying some more applied physics and more known physics to the experiment to begin to understand things. And it's also going to take us in another direction of beginning to move in the direction of figuring out what's going on microscopically. So if you have a chemical reaction, for example, if you have combustion of methane, you produce CO2, you produce H2O, and if you make a fair amount of energy, you can make a fair amount of products. So for example, in Fleisch and Pon's experiment we talked about on Monday, the amount of energy produces 630 kilojoules. Now, if you believe that that energy was produced chemically, and we can have methane burning as an example of a chemical reaction to stand in, then 630 kilojoules would give you 0.7 moles of CO2, 1.41 moles of H2O. And in general, chemists are very good at seeing small amounts of products. for example, if you have combustion of either wood or gasoline, it turns out that you guys come equipped with your own chemical sensors. You can smell some products of reaction. I think CO2, H2O are not easy to smell, but there are other products which are much easier to smell. So basically, the argument is if in Fleisch-Pon's experiment, with so much energy being produced, it would be very easy to see chemical level reaction products. But as we remarked before, they're not seen. So that motivated Fleischmann to conjecture that we're seeing energy of a nuclear origin. Now, suppose we had DD fusion making neutron plus helium-3 or proton plus triton. So 630 kilojoules over, call it 4 MeV. We get this many reactions. The question is would we be able to see that? And as I pointed out before, here's an experiment of the Fleischmann-Pons and the cell, and there's no lead shielding. Well, it turns out that for neutrons, the energy, kinetic energy in neutrons is important. So 1 gray is sievert, which is 1 joule per kilogram of irradiation. So if you were getting a watt worth of neutrons coming off and you're standing close to it, you're going to get very serious medical problems in a relatively short time of exposure to such a high level. So if you like, we have neutron detectors. We have 3 neutron detectors here that are sensitive at this level of conjecture neutron production. So we can see that we don't have neutrons at the level, at the watt level. We have also real neutron detectors that I'll be talking about shortly that are going to give us a much lower band. So if there's not, we're gonna make arguments that aside from neutrons, gammas, tritium, other things, there's not going to be commensurate energetic nuclear radiation in connection with the energy produced in Fleischmann-Pons. You can use that to say, well, we can rule out nuclear as a source for the energy. So that means it has to be error, which is the argument was made by Caltech, by MIT, by Zenga, pretty much everybody else back in 1989, 1990, and even to this day. But suppose we say that we're dealing with something new, that maybe something's happening that we're not familiar with. Suppose it happened anyway. Suppose that some reaction was going on and there are going to be nuclear products. Suppose these nuclear products happen to be stable. How many of them are we looking for? So 630 kilojoules are bound to be DD fusion making helium-4 in some way that nobody's ever seen before. We'd be looking for this many atoms. And this many atoms can be seen, but the job of seeing it becomes harder. Especially if instead of helium, if you're looking for silicon or oxygen or other things which is already in the environment. So in general, for a nuclear process, we don't expect a particularly large number of product atoms. Now, this was a very serious issue. Back in 1989, when people were first seeing excess heat, we didn't know what the product was going to be. Helium-4 was looked for, lithium isotope differences were looked for, other metals were looked for in the palladium, and perhaps the palladium was fissing somehow in a way that wasn't going to produce energy. So a very large number of studies was done, a very large amount of money was spent on assays, just simply looking for products. And the headache is these materials are impure, so there's all kinds of stuff there. So you start the experiment, you take the palladium before the experiment, you analyze it, you do your electrolysis, you analyze it afterwards, and you get this gigantic list of everything that's changed, including a laundry list of 25 different elements that are now present in your experiment that weren't before. And you look at that and you say, well, are these contaminants or were they made by some new process? Not a very fun way to do your research. Takeaway message so far. We expect products from energy production. You don't get energy for free from nothing. It doesn't just magically appear. So under discussion is a reaction process that's going to have products. We can't really proceed unless we start with something like that. If it's chemical, we expect lots of products, experiments none commensurate with the energy you're seeing. If it was energetic nuclear products, it would be very easy to see. We put a detector there, we settle it, 15 minutes later we know what's going on. Well, that's not the case here. Non-energetic nuclear products, which is what we have to contemplate given the experimental situation, that's tough. Very large number of unsuccessful searches were done. I saw results from many of these. However, there's light at the end of the tunnel in the case of helium-4. I'm interested now in helium-4. In 1989, there was discussion that maybe deuterons somehow make helium-4. What we only found out later on is that Fleischmann apparently had detected helium-4 back in 1989 or 1990 in the gas phase. We didn't hear about that at conferences. It wasn't published, and it's only in personal communications and years afterwards that we learned from Fleischmann that he had done it. We know that there's a weak branch in conventional fusion of DD going to helium-4, which is accompanied by a gamma ray taking most of the energy away. Helium leak-tight systems, if you want to assay for helium, that's not easy to do. You need somebody who's a specialist in helium measurements in order to work with one of these cells to make it work. Low-level helium detection is not the world's easiest thing to do, but it can be done. Big headache is there's background helium-4 at level of 5.22 parts per million in the atmosphere. And you had argued on Monday about the gigantic theoretical problems from condensed matter physics and nuclear physics. Well, if you think you got helium-4 without gammas, and there are not commensurate gammas of 24 MeV coming in the experiment, then you have you're confronting a major problem with nuclear physics if you're going to think that you're going to get helium-4 out. Helium-4 does come out in conventional DD fusion experiments. One of my friends at Cecil did a publication where they did an experiment with a beam coming in DD fusion, and they were looking at the helium-4 branch, and here you can see some 24 MeV gammas on a sodium iodide detector. They're there. And here's the yield of them. This is 10 to the minus 10th, this is 10 to the minus 5th, this is the center of mass energy. So if you come in at very high energy, you sort of get a higher yield of them. You come at lower energy, you get a lower yield of them. And there's the numbers for your zero energy. So we get roughly 50-50. Now there's Oppenheimer-Phillips, so you get a little bit more of one than the other. The helium-4 branch is down at 0.6 times 10 to the minus 7th. So it's smaller because it's mediated by electromagnetic interaction. These guys are mediated by strong force interaction. So there is a way to make helium-4 in nuclear physics, but you get the gamma out, which is not seen in cold fusion experiments. To measure helium-4, you have a headache that helium-4 has a low mass. A little bit higher mass is D2, so you need a good mass spectrometer to separate the helium-4 from the D2. This is data shown under conditions where the amount of helium-4 and the amount of D2 are roughly commensurate. If your helium-4 is just a really tiny amount and you've got lots and lots of D2, then this gets really big, and this isn't going to show up if this guy's really big. So when you do your measurement, you have to reduce the amount of D2, so you need traps to make it work better. And anyway, so you can see helium-4 a good mass spec, interference, lots of technical issues, atmospheric contamination. Also, helium-4 goes through metals and glass, which is what makes getting a helium-4 leak-tight system tough. So that's the problem. What's the response? Well, the response is to take some folks with expertise in Bush and Legowski had expertise in helium-4 detection, and Mel Miles was an expert in getting, his electrochemist was an expert in getting excess heat in cold fusion experiments. So they set up a cell, and they basically got gas samples, cryofilter, more cryofilters, you reduce the D2, you send it off to the mass spec, you do measurements, and what they found was for light water runs, they saw no excess heat, and they saw no helium-3 or helium-4. For heavy water runs, they saw excess heat, and in many cases they got helium-4. And what was interesting is the amount of helium-4 they saw was a lot. It was seen in amounts that could be commensurate with the amount of energy that was produced. This is an absolutely gigantic result. I mean, I presented this and I talked about this time and time again, and I'm thinking back and I'm thinking, back in the early 90s there were actually some resources and there's some very good people. This is just, this first observation, the fact that it could be done and was carried out, gave a result is stunning to me. So helium-4 comes out in amounts commensurate with the energy produced. This was found by Miles and Bush and co-workers. There was a tremendously good Italian experimentalist by the name of Daniel Gozzi, had a group and had experiments that showed an incredible amount of imagination, creativity, and scientific excellence. Basically, you have this ring with lots of calorimeters in it, and basically high-power calorimetric systems. He spent years working with some colleagues who were experts in helium detection, and after, I don't know, is it 3 or 4 years worth of development, they were able to do some measurements. And what was different about their measurements is that they had time-resolved measurements. They set things up such that they could sample sort of in real time. And here's an example of measurements done showing at t = 0, they put some helium into their system, and 200 seconds, 400 seconds, you could actually see the helium, so it's now time correlated with the production. So the idea is that if you have a heat burst, when the heat burst happens and you measure helium, if you correlate the helium in time with the heat burst, that's interesting. That would be reasonably convincing. So here's data, and here's time in hours. Here's a big heat burst, and the big heat burst over here, here's 5 watts, 10 watts, 15 watts. So this is a substantial heat burst. Up here on this axis is number of tera atoms, 10 to the 12 atoms of helium-4. So heat burst, helium-4, heat burst, helium-4, heat burst, helium-4. This is in black and white. When Gozzi first presented it, it was in color, so color somehow makes everything look much more real. I was looking at it, Mike McCoubrey was sitting next to me, was looking at it, my jaw drops and hits the ground. Look at it, I thought, wow. This at the time was just amazing.
When was this done?
This was done roughly 95, 96, something like that. Publications, do I have the reference for that? Yeah, here's 1998, publication 1998. It was presented before it got published.
Did you present this information on the helium-4 in the DOE review, the later one?
I had 45 minutes to present everything I was going to present. So. Takeaway message. So for energy production, we've got to have an ash, or Mike hates the word ash because ash means you burn wood, there's ash remain, but the chemical products is CO2, H2O, the gases, so ash isn't quite right. There's got to be a product. chemical products would be impossible in this context. There just aren't there. Commensurate energetic nuclear products would also be impossible in this. They are not there. Many unsuccessful searches for isotopic anomalies. Helium-4, and I'll be talking even more about helium-4 measurements, but helium-4, in the case of Fleisch-and-Pond's palladium deuteride experiment, is seen in amounts correlated with the energy, also time correlated as we've seen, and also without commensurate 24 MeV gammas. The gammas are not there. Takeaway message: I get to catch my breath. You get to ask me questions.
There are some cases helium-3 came out in the previous slide, and I was wondering in which cases helium-3.
Which slide are you referring?
That was there was a list.
Oh,
There were,
this, for example, no
Three
helium-4.
motions.
Oh, in the Bush-Miles experiment, looking for helium-4, helium-3.
Yeah, okay.
No helium-3.
And the next one, perhaps.
This is also
Yeah.
helium-4.
Okay, I see. So no helium.
No helium-3, no helium-3, no helium-3, no helium-3.
Oh, okay.
Helium-3 has not been identified as a quantitative product connected with energy production for palladium deuteride.
What about tritium?
Sorry, what?
Tritium, is that the same as one of the possible products for the branches?
Your question's a fantastic question. Tritium has been observed. Tritium's been observed repeatedly. Tritium has been observed in electrochemical experiments, Fleisch-and-Pond's experiments, showing excess heat results. Tritium's been observed in blow discharge type experiments and gas flow experiments. Tritium production, which you might think would be a potential product of, of P plus D, P plus T final branch, but in that case, you'd expect the tritium to have energy. I'm going to talk about this shortly. And if there's D in the environment, then energetic T hitting a D would give you DT fusion 14 MeV neutrons, and that's been looked for, and they're not there. So T is observed, but it's not from the conventional energetic 4 MeV P plus T branch. But there is, in general, in the Fleisch-and-Pond's experiment, you do measurements for tritium, you don't see anything. Under some conditions, specialized conditions, you can't get it. Mitchell actually clarified the big issue. Back in the early 90s, I was thinking along similar lines of Mitchell with respect to the optimal operating point. So the argument was there were reports of neutrons, reports of tritium, reports of excess heat. Let me imagine there being a line. And for the Fleisch-and-Pond's geometry in lithium deuteroxide, the question is, what's the current density, electrochemical current density associated with each? So for example, neutron production was reported between 10 and 30 milliamps per square centimeter. Tritium production was reported around 70 milliamps per square centimeter. And excess heat production seemed to me 200, 300, 500 milliamps per square centimeter. So it's almost as if you're dealing with a system that can be run in different modes. You run it in a mode of high current density, run Fleisch-and-Pond at high current density, you see excess heat, no tritium. You run it at lower current density, you see tritium, no excess heat. The experiments in which tritium and excess heat are seen are experiments which actually go between the two regions. And then there are other experiments, there's low-high experiments where they run low current density, high current density, low current density, high current density. So high current density, you see excess heat, low current density, you see neutrons in those
the
experiments.
tritium is seen is in very low quantities that wouldn't be expected to produce substantial heat, or is it just a trace, or?
It's produced in amounts much lower than would be commensurate with the excess energy. On the other hand, in some experiments, it's produced in ridiculously high amounts, absolutely. So 10 to the 16th tritium atoms in some experiments.
Look at you saw the second graph of HE4, there was the mild and push graph. Who did the experiments for the second one that you said was it color originally?
Daniel Gozzi's group, University of Rome Sapienza. So there's the reference. Okay, Well, if you like, this now changes everything. We have a product. We have helium-4 as a product, which means we can start beginning to move in the direction of dreaming up a microscopic picture. I mean, without a product, we're chasing ghosts. But now if we have a product commensurate with the energy, now we can begin making use of laws of physics to see how it works in connection with this experiment. And before doing so, the big question is how much energy are we talking about? If you have a product, well, you ought to have an energy. So for example, conjectured early on by Fleischmann was 2 deuterons are somehow coming together in some kind of new way to make helium-4. Well, if that happens, the mass energy of 2 deuterons minus the mass energy of the product helium-4 is 24 MeV. This is the mass energy number. So if in fact deuterium's coming together making helium-4, you're making helium-4, well, if you measure the total amount of energy that you make, and you measure the total amount of helium-4 produced, then you have a reference number you can check to see the amount of energy is 24 MeV per helium-4. If that's true, then you can begin thinking about a deep to helium-4 kind of branch. So this number is a very important number. So the question is, what do we know about the number? Now, one of the first experiments that's relevant to this is an experiment that was originally pioneered by Les Case, who is sadly no longer with us. Les Case had catalyst, a small amount of palladium on a carbon-based catalyst. You load it with deuterium and at elevated temperature, and Case saw prodigious amounts of excess heat. And Case sent his gas to be analyzed, and his gas showed more than 100 ppm of helium-4. So this was a stunning result, because now you have an experiment that produced a lot of heat. Looks like it produced helium-4. So if you can measure one, measure the other, and correlate them, you have the chance of measuring the reaction Q value. So at SRI, they brought Case over, and Case taught them how to do his experiment, and they had a mass spec, so they had the possibility of measuring energy produced in helium-4 in the same experiment. So they did a series of experiments. This is an example of the helium-4 measured during an experiment. So several experiments. So what was observed is helium-4 was produced. This is the level of helium-4 due to atmospheric contamination. So this is 5.2 parts per million inside the cell. There's less of that to start out with. Helium-4 is liberated an amount that's larger, and then it starts to go away. Question, where the heck is it going? Apparently the catalyst soaks up helium-4. So if the catalyst can soak up helium-4, well, is the catalyst leaking helium-4 initially? Well, they did some tests, put the catalyst in and heated it up to look to see if helium-4 comes out. Helium-4 apparently doesn't come out of the bare catalyst. So the thought being is that this helium-4 perhaps is being produced by the reactions. In this case, you can measure the energy produced, you can measure the helium-4 produced, and results from these kinds of measurements look like this. So here's time. The red is the red and the gray are helium-4 measurements, and helium-4 measurements converted into excess energy. Actually, not excess energy. Okay, I don't have the units here. The units here are related to the number of helium-4 atoms. The blue and the green, this is the energy produced as measured by 2 different kinds of calorimetry. So what you're supposed to look at and see here is that the energy production curve and the helium-4 production curve seem to match one another. I mean, you would prefer a differential of this, so if you get a heat burst, then you get a helium burst. that this measurement was done without the nice time resolution that Gauzy had for his system. So from that, you can plot helium increase correlated with the energy produced. So you get experimental data points, and you can draw some lines through it. And the lines through it, the hope is 24 MeV per. What we see is 31 or 32 MeV per reaction. So we're not getting 24 MeV. We're getting a higher number. Scratch your head and you say, well, that's discouraging. What reaction happens at 30 MeV? Well, of course, there isn't any DD to helium-4 reaction that occurs at 30 MeV. So we hope to see 24 MeV for helium-4 if it's the DD going to helium-4, which we don't know at this point in the argument. Case experiment shows 31. Now go back to Gauzy's experiment, because Gauzy had different heat bursts, and he measured different amounts of helium associated with the heat burst. And he tried the 24 MeV number also. And what he found is one burst would give half the amount of helium you'd expect, another one would give 2/3, another one would give 1/3, another one would give darn near 100% of the amount. And when Mike and I were looking at that, we're saying, why should there be a different amount of helium-4 each time? Mike said, well, obviously, so the helium is being retained in the solid and not coming out into the gas. We're not getting to see all the helium-4. So the conjecture is helium-4 retention, that if we did a better experiment, if we could scrub all of the helium-4 out, do a measurement, maybe we'd get a number closer to 24 MeV. Okay, so this draws our attention to an M4 experiment done at SRI. So this is done in a helium leak tight system. So we're going to look at this. These guys are measured values. The green things is going to be a parametric fit, which I'll talk about shortly. This is the current density. So if you like, here's a current step going up. And that's the way, like, at that time it produces excess heat burst. You get a current step that induces excess heat burst. It gets a second one back here. But this is done on a helium leak tight system. So you can analyze the deuterium, look for helium-4, and correlate it. So he knows how much energy is produced. He's got an accurate measurement of the energy production. And he's got accurate measurements of helium-4. So in connection, so this line shows you take the energy produced and you turn it into number of helium, the helium concentration that you would expect, assuming 24 MeV. So this is what you're hoping to see if it's DD going to helium-4. The first measurement's done here at the end of the second heat burst. So 62% of the amount of helium-4 that you'd hope to see based on the 24 MeV number is seen. So this is sort of consistent with the case experiment measurement. It's sort of consistent with some Gauzy's measurements, consistent with other measurements in the field. So I say, well, let's be patient. So next day, take another sample. A little bit more helium-4. So instead of 62%, we're now at 69%. More patience. Another measurement. Well, not much extra helium-4. So what is going to come out easy is coming out. So now you want to get the rest of it out. So you have to start using, I don't know, waterboarding. No, not waterboarding. They don't use waterboarding like that. You come in, and one technique is to go ahead and run the cathode anodically to remove the deuterium. The idea is that as the deuterium comes out, maybe it sweeps the helium-4 out. In addition, heating the cathode can also help remove helium-4. So this was done, many cycles were done. The helium was assayed again, and the total number now comes up to 104%. So in this experiment, an effort's made to pull out the retained helium-4, and when this is done, we now get a number which is basically consistent with the 24 MeV Q value number. For a long time, this was the only experiment of its sort. So it gives the 24 MeV number good to within about 4%, which is basically the accuracy of the measurement. Uncertainty near 10%, all that's, you talk to Mike and Mike says it's 4%. There's one other experiment that's been performed that's qualitatively similar. So at Ennea Frascati, this problem was of interest. They were doing laser excitation. So they had 3 experiments. These experiments, laser turns on, stimulates the excess heat. These 3 were done in a helium leak tight system. And in this case, this amount of excess heat was observed. This amount, excess heat was observed. This amount of helium-4 was observed. This is the amount of helium-4 that you would hope to observe based on the amount of energy that was produced. But in this experiment, there was no effort made to scrub out the retained helium-4. So between here and here is maybe you're getting 70% of the helium-4. Same thing over here. Amount of energy, helium-4, you're getting 70+% of the helium-4 that you would expect to observe based on the energy. Now here, you have a different experiment where energy was produced, helium-4 was observed. But in this experiment, an effort was made to scrub all the helium-4 out. So in this case, the experiment in theory, experiment in the expected value, scrubbing out all the helium-4 is giving the 24 MeV number. Now, a problem with this experiment is that there's a line here which says background, and this is the 5.2 part per million background. So in fact, it's more like this. It's not from down to here, it's from here to here versus here to here. So this, I know this is under 60%, and this is maybe 60%. So these numbers are close to the others. But this one is, again, you scrub out the helium, you see it. So there are now 2 such measurements. There's no resources, in all this time to do more measurements. I had a discussion with the funder. I said, well, we could use some of the funding to do this measurement. So, well, if you do, you're going to go to jail. So you have to use funding for what the funding's allocated for. You can't use funding to do measurements that need to be done because they're the right thing to do. Takeaway message. So DD goes to helium-4, we'd expect 24 MeV for a Q value. Experiments, and this is an experimental question, it's not a theoretical question. You have to go to the experiment to see what the Q value is in the experiment. We've got the helium-4 retention problem. We've got 2 experiments now with scrubbing consistent with 24 MeV. And 2 experiments is not really enough experiments. I mean, at the moment it's consistent. It's interesting. The SRI experiment is the most accurate of the experiments. And we needed 20 more experiments done really well, done carefully, to be sure that this is what's going on. So we have consistency with DD going to helium-4. We do not have proof DD going to helium-4. And I underscore once more, theoretical issues loom large for DD to helium-4 explanation because they're not commensurate 24 MeV gammas. Okay, takeaway message slide. So questions, easy questions only, no hard questions.
There are no 24 MeV gammas, but the energy adds up to a number of.
That's right. So the total energy, thermal energy measures 24 MeV per helium-4 is the conclusion from these 2 experiments, but that energy didn't start out as gammas.
Yes, for easy questions.
Thank you. Much appreciated. Other questions or comments?
So basically,
Go ahead.
so like, you said the problem was that you had an energy gap that you expected 24 MeV, but you measured, you thought like you're just not chasing all the helium out of the experiment. It's hard to detect with your detectors.
No, the issue is that the detectors are pretty good at seeing the helium that's there. The issue is that when the helium is made, presumably it's made inside the cathode, some of it leaks out, maybe not all of it leaks out.
I may be getting ahead of what your lecture plan is on tomorrow and Friday. But will you be presenting any information about the nickel system? Thank you.
Friday's focused on nickel hydrogen. I mean, we've been talking about issues all along. We'll continue talking about issues along, but we'll have a dedicated discussion of nickel hydrogen on Friday. Okay. Excess power versus temperature. This argument's, in my view, related to helium, but it's sort of a roundabout way to get there. Fleischmann and Pons, they found the effect initially, and during the years that they were active, they did a set of stunning experiments, absolutely stunning experiments, and stunning suggestions. This is one of them. At issue here is a protocol that Fleischmann and Pons used that other people weren't aware of until ICCF3 at Nagoya. Fleischmann got up and explained it. So here it is. So Fleischmann says, okay, so we start out at low, at this point, so the cathode's presumably been loading for a long time, so at this point we're going to crank up the current density, sort of 200 milliamps current, and you see these bumps here. Maybe you see these bumps here. There's bumps here. And these are calibration pulses. So Fleischmann was kind of a nut about calibrating. Not a nut, that's not the right word, but he wanted to see, he didn't believe the calorimetry unless you verified it with a calibration pulse regularly. It's a little bit like Mitchell with respect to putting in a lot of calibration pulses. So calibration pulse, calibration pulse, calibration pulse. And what Martin noticed was that when excess heat was being produced, that the calibration pulses made the heat go higher. So you in this experiment, you do your loading at low temperature because you can get higher loading more easily at low temperature, but the excess heat effect seems to be more efficient at higher temperature. So what he did is he used his calibration pulses to help nurse the temperature to higher and higher, which increased the excess heat output. So under Fleischmann-Pons protocol, you could get a much higher level of excess heat production than using more pedestrian protocols. For example, to do a good measurement, maybe you want to work at constant temperature. If you work at constant temperature, if your temperature is low, you can load well, but your excess heat's no good. Constant temperature is high, you can't load very well, but if you do get loading, you get the temperature enhancement for the excess heat. So let's look at what Fleischmann was looking at in detail. So I'm looking here at the temperature profile in the case of a calibration pulse. So here's the temperature rising during calibration pulse. Temperature comes back down. And if you think about it, the calibration pulse is an increment over something larger that the cell is doing. So the cell, in this particular case, cell temperature is dropping. Calibration pulse happens, but it doesn't impact the dropping of the cell temperature. So this is done before an excess heat burst. After an excess heat burst, the same kind of thing is observed, that temperature is coasting down, calibration pulse, the temperature relaxes back to where it was pulsing, was coasting down. During excess heat burst, so under conditions where the cell's producing excess heat, Fleischmann comes in, temperature is going down, calibration pulse, temperature relaxes back down to sort of a similar level, but that level now has got an temperature increment increase. Namely, what has happened here is that the calibration pulse has given him an increase in the excess power level. And like I say, I was in the room watching this and it's being presented. My jaw drops. My jaw drops a lot to pick my jaw up and put it back. here's another observation of the effect. This is done by Dennis Cravens in a very different experiment. So here's his temperature baseline here, calibration pulse, and then temperature following the calibration pulse. So the calibration pulse, by being present, has raised the amount of excess power being produced. So the question is what's going on and how do we think about it? Calibration pulse increases the cell temperature. Excess power is higher afterwards. Fleisch and Pons used this as a way to develop a protocol that was much more effective in increasing the excess power in their cells. The implication is the excess power is nonlinear in temperature. Basically, you get more excess power at higher temperature. So in Fleischmann's protocol, you get the high loading at the low temperature, but then you get the high excess power at the high temperature. You can load, if you can maintain your loading line, raise the temperature, then you can take advantage of this nonlinearity to get more temperature or more excess power out. There were a number of measurements of the dependence of the excess power as a function of temperature. This is data from Ed Storms. So it's a relatively limited temperature range. But the excess power is seen to, again, this is a funny plot, but as the temperature goes up, the excess power goes up. And Storms fit it to this particular form. So it's e to the minus delta E over KT. Sort of the idea being is that maybe there's some kind of barrier associated with energy production. And the delta E was found to be 673 millivolts. So excess power in a number of experiments was found to scale in this way. Storms got 673 millivolts. Mitchell got 715 millivolts, basically a very similar number. Case got close to 700 millivolts for temperature scaling at much higher temperature. So, we basically like some systematic data over larger temperature range to really be sure. I mean, the temperature range isn't enough in this, but there's enough here to motivate us to wonder why the excess heat varies with temperature. So the first point, just for kicks, let's take e to the minus delta E over KT with Storm's number and make a plot of it. Here's 300C, here's 400C. It's 1 order of magnitude, 2 orders of magnitude, 3 orders of magnitude. This is a big effect. And we're not talking about 5% or 10%. We're talking about factor of 10 increase, another factor of 10 increase. And if you can really load and then raise your temperature and operate at higher temperature, this is a big deal. This is a way to get much more excess power out of your system. Now, the question is, why should there be an e to the minus delta E over KT dependence? In the early days, folks were thinking, well, the delta E here is the barrier for the nuclear reaction. I'm thinking to myself, barrier for nuclear reaction less than a volt? No, not going to work that way. But on the other hand, suppose that we've gone to a lot of trouble to make a vacancy, a mono vacancy, and suppose we've gone a lot of trouble to load or cap it up to get a D2 there. Suppose that D2 actually is reacting to make helium-4 in some new way that nobody has any idea about. Now suppose you got helium-4 sitting there. Suppose now you want to have another reaction. You've got to get rid of the helium-4. It's an analogy. It's cold. You want to be warmer. You make a fire. Well, did you clean out all the ash last time you made a fire? If you didn't, then you're not going to be able to make a new fire. So if you're making helium-4, helium-4 is plugging up your vacancies. Then you've got to get rid of it before you're going to be able to put new helium-4 in.
But I mean, question. Doesn't that also drive out potential potential atoms that might react when you heat it up?
Maybe you don't take my analogy quite as much. I'm not getting rid of all gas, hydrogen, deuterium, helium-4. The idea is that if you can get the helium-4 out of the trap, then it's going to diffuse to the nearest surface. When it reaches the surface, it can leave. So the diffusion through of helium-4 through palladium was computed by Zia, and basically the barrier number calculated was 720 millivolts, which basically is the same number as Mitchell got, and essentially the same number as Storms gets. And you can calculate the diffusion coefficient as being this. This is not the world's largest number. It's actually hard to get helium to move through the lattice. So, for example, here's Storms' number, here's the Zia's number for helium, and I'm looking at that, and I'm looking sort of close to me. So the conjecture here is that the temperature dependence could come about if you have a system that's working really, really well, so it's making so many reactions, it's making so much helium-4 that the helium-4 is plugging up all the vacancies. And then you're going to try to get the helium-4 out of the vacancy and then diffuse it towards the surface. So this also implies that getting it out of the trap initially doesn't take long relative to the diffusion time for a surface. So let's calculate the. I did a simulation where I said let's source the excess heat at a certain location away from the surface. Let's go ahead and solve the diffusion equation. See how much comes out. See how much goes in. Never comes out again. And here's what the numbers look like. For example, if I'm 1,000 angstroms in from the surface, and if I do a measurement 1 hour later, and if I don't have any deeper traps or anything that's going to keep the helium-4, then in this case, most of the helium is going to stay in the cathode. So I look at this, and I'm thinking that, if I want to do a measurement of helium-4 production in the gas phase, if the gas comes out reasonably fast, and if it has to diffuse from the point where it's made out to the surface, then by figuring out how long it takes the helium to come out, I can go ahead and put an upper limit on how far in from the surface it was. In Godsey's experiment, I don't remember the time axis, but it was measured in units of hundreds of hours. So in Godsey's experiment, the resolution was around here, somewhere here. So I go here, and I say they got maybe half of it out, then I'm up here. If I go over here, I'm talking about maybe 2,500 angstroms in from the surface. And that's not a lot. In some of the other experiments, the numbers are here. So, I'm sorry, 10 minus 6, 10 minus 5, 10 minus 4. So on the order of 1,000 angstroms from the surface would be consistency with the helium-4 going into gas phase measurements. And if you like, this is interesting because this is consistent with this co-deposition picture, that to get the vacancies, you've got to have the high loading above 0.95, you co-deposit on the surface. Well, how much do you co-deposit? The Fleisch and Pons experiment, the measurements, you co-deposit 1,000 or a couple thousand angstroms of material. So this seems to be a plausible explanation as to why you would see temperature dependence in excess heat experiments. Mind you, not in all excess heat experiments. For example, suppose you had an excess heat experiment where the amount of helium-4 production was not sufficiently high enough to plug up the vacancies. Well, in that case, you wouldn't see any temperature dependence. So there are experiments where temperature dependence is measured, but there's no temperature dependence. On the other hand, in Fleisch and Pons experiment, things are working really, really well. The notion that under those conditions that you're plugging up all the available vacancies with helium-4, then that would give you the temperature dependence to associate with diffusing the helium-4 out. Well, when I think about nanners, on the order of half an hour or more, Mitchell was going to delight us with a discussion of his nanotechnology. So the question is, if helium-4 accumulates in active sites and and poisons them in the sense of not allowing further reactions to happen when all the active sites are filled up. And if that's responsible for the temperature dependence, then maybe if you make the distance between the site and the nearest surface where you can get rid of helium-4 smaller, you'd be able to work at higher power, because dumping the helium-4 would be far more efficient in a smaller scale system. So I'm proposing that this is perhaps the physical base of the source of the advantage of nanoscale systems. Now, of course, Arata has been pursuing nanoscale devices for ages and ages and ages. And I guess I've been arguing this for 5 or 6 years or more. I guess at one of the recent conferences, Arata proposed basically the same kind of argument. So his proposition is independent of mine, but I think mine's a few years before his suggestion. So the idea is that you've got a big cathode. If your excess heat's made inside here, your helium's got to go a long ways to reach the surface. But if you've got nanoscale palladium, and if it's in a matrix of some sort, if you get your helium from the site where it's produced a small distance to your matrix, and if your matrix is capable of communicating it elsewhere, then this system's going to have the possibility of running at much higher power density than this system. So an interesting experiment would be to test the temperature dependence of a nanoscale system, and also see if the excess power scales in a way consistent with diffusion as a function of nanoparticle size.
But this may be a very basic question, but how can helium be taken out when it's in nanostructure? And also, how small does that nanostructure needs to be?
At the level of the argument today, in terms of size, there's sort of a simple scaling that the excess power is going to go by the inverse size scale length if it's diffusion dominated. So basically, making it smaller helps, making it even smaller helps. I'm going to leave to Mitchell to talk about his experience with respect to how well these things work as a function of size, if he chooses. In terms of how you get the helium out, we've talked about diffusion from the metal to someplace else, but you still have to get it either going through or diffusing through to someplace else. So if the matrix itself is an imperfect matrix, if it's got crevices where you can have just helium flow out, that's incredibly efficient. Helium basically passes through almost anything pretty reasonably quickly. The headache is if you've got the deep traps. If you've got a lot of electrons around and you've got deep traps, then it's hard for it to move. On the other hand, if you've got an insulator, so you don't have a lot of electron density around, and you don't have a lot of embedding energy, so it has a potential to move in much more quickly. There's another question.
Yeah, my question was that was working if zirconia was had a large diffusion.
Again, I think zirconia is going to have a low electron density. Helium is an atom, is pretty small. So I haven't looked up the number. I would expect the diffusion of helium through zirconia to be pretty good. Does anybody have a number for that? No? Okay. So takeaway message. Observed temperature dependence in these experiments seem to be consistent with helium diffusion. Propose that helium fills up vacancy sites and provides an upper limit for excess heat production, provides a mechanism for limiting excess heat production. Consistent with the picture we've been building up of formation of vacancies by co-deposition on the outer surface. In future experiments, if some of my friends are optimistic and believe that there's going to be resources available. I'm less optimistic, but if I for a moment entertain the fantasy that there will be resources, then in a future experiment one could correlate helium-4 release time and active layer thickness in experiments and help build up evidence to see if you've got a big thick layer and if you're running high excess power relative to that thick layer, is your power level limit at one point, and then you make it factor 2 smaller, does your excess power go up by factor 4? As an experiment, that would be, it's a doable experiment. It'd be interesting to see. And if you can measure the release time and correlate that with the distance and connect that with the diffusion of helium through, that would add evidence that this is actually going on. The scaling is favorable for applications at elevated temperature. The effect basically gives a gigantic leg up for smaller scale devices.
What effect would you expect for elevated temperature on the formation or the loading or the formation of D2 in these little preferred vacancies?
It hinders it, but I think it's a weaker effect than helium diffusing out if it's plugging things up. There's a recent paper that's going to show up in the CMS journal. It was conference proceedings for the ICCF by me and Letts, and there's more experimental data from the 2 laser experiment. We were analyzing it in terms of the temperature dependence, and it's possible that what Letts saw in that experiment is a second delta E, which might be corresponding with getting out of the first trap. I don't know, but he saw evidence for potentially a larger delta E being involved for the highest power level experiments. Okay, so we've had some questions here. Are there other comments or questions? If not, we'll go zooming on. So what I want to do, we now have helium being made. We've got some notion of the Q value. And what we'd like to do is take another step towards applying conventional nuclear physics ideas to try to untangle what the measurements mean and try to move towards getting a microscopic picture of what's going on. The place we're going to start is with Rutherford. Back in the dawn of nuclear physics, Rutherford gained fame and advanced nuclear physics dramatically with the experiment involving alpha particles scattering from a gold foil. Everybody's seen this, probably at high school these days. But large angle scattering events were seen, and large angle scattering events were consistent with a billiard ball kind of picture of nuclear physics, and implied that the nucleus is a very small object. So the Rutherford picture is one in which nuclei act like balls on a billiard ball table. So you have your ball coming in, it strikes another ball, one goes off one way, one goes off the other way, and you can figure out that you can relate the kinematics through conservation of energy and conservation of momentum in a classical billiard ball picture. So the billiard ball pictures, it's wonderful, it's compelling, it gives us a way to visualize what's going on the microscopic scale in terms of things that we can hold in our hands and get intuition about. Okay, so the picture can make use of conservation of momentum and conservation of energy. Conservation of momentum, initial energy plus reaction energy, if any energy is made, gives you the final energy. So if you solve these, you can figure out what the final state energy of the particles are in the reaction. So for example, if 2 Ds are sitting next to one another, if they tunnel together, they react, they're going to go zipping off in different directions. And you can relate the final state energy to the mass by studying the kinematics. So for example, if you have 2 deuterons fusing, making helium-3 and a neutron, then the helium-3 gets one amount of energy, the neutron gets another amount of energy, the neutron's lighter, gets more energy. It's one of these things, if you take a ping pong ball and you throw it against a truck, the ping pong ball is going to bounce, the truck's not going to move, and that's intuitively where momentum and energy conservation comes in. So for example, if I take 2 deuterons in initial state, say in a D2 molecule, Suppose now that they react and they fuse, and you make 3 plus 1. Here's 3, here's 1, maybe helium-3, maybe a triton, maybe a neutron, maybe a proton. Then you can solve for the, if you start out with no energy, and all your energy comes from the reaction energy, then you can figure out that the particle mass 1 particle, in this case, the lighter particle is going to get more of the energy. The heavier particle is going to get less of the energy, and the energy is going to be split basically according to the mass of the other particle. So the M1 kinetic energy depends on the mass 2 over the total mass. The mass 2 is going to depend on mass 1 over the total mass, and that's how it splits it up, and that's a consequence of energy and momentum conservation. So Rutherford picture's fantastic. It allows you to understand how this stuff works sort of trivially. And it's important. It's nice to know that on a microscopic nuclear scale things are called billiard balls. That's like, that's great because it allows us to think about it sensibly, rationally. We don't have to think about some mysterious, etherical event going on. We got conservation of energy, momentum, and billiard balls we can understand. Now let's apply this now to a reaction which was proposed to account for Fleischmann-Pons effect. For example, I was invited to Naval Postgraduate School for a few months to have a study group on cold fusion theory. So we studied, and towards the end of it, we gathered together some senior physics folks to try out arguments on it. I gave them all kinds of very clever, sophisticated arguments. And at the end, one of the senior theoretical physicists got up and he said, all of that's junk. It doesn't work like that at all. What's happening is 2 deuterons come close to one another, they push off of a palladium nucleus and go off as a helium-4, and that's how it works. So what I want to do is, in honor of this very famous theoretical physicist, I want to think about this proposal in light of the Rutherford picture. So now we've got 2 deuterons. Instead of being next to palladium, we're going to have it be next to X. So X can be palladium, X can be a deuteron, X can be a WIMP, X can be whatever. And what I want to do is I want to think about Rutherford, conservation of momentum, conservation of energy. When these guys come together and helium-4 make 24 MeV and push off of the mystery X. If this happens, then I can use conservation of energy and momentum to figure out that the helium-4 is going to have a kinetic energy, which is going to be 24 MeV, divided by, or times the mass of X divided by the total mass. So this tells me that if I can figure out from experiment what the energy of the helium-4 is, I can figure out what X is. What do you think?
I like that.
Okay, so we now have a new goal in mind. We want to know what the kinetic energy of the helium-4 is, of the alpha particle is when it's formed. So here's my takeaway message. Basically, we can learn something about what's going on microscopically if we can measure. Takeaway message time for questions. Time for me to catch my breath. Are there questions? No questions. It's clear what we're going to try to do.
Okay, so you're saying then that the 24 MeV does not appear as a gamma, it appears as kinetic energy of the nuclei.
No, I'm not saying that. What I'm saying is that this very famous theoretical physicist argued that this is the only possible way it could happen.
Well, you're not saying that that's actually happening. You're just saying that that's what we're talking about right now, the possibility.
But there's a picture on the board, and it's a picture which is testable. So what I'm going to do is see if we can test it. So now we're interested in measuring the helium-4 energy. So you review the argument. 2 deuteron mass energy of 2 deuterons minus mass energy of helium-4 is basically 24 MeV. So now we're thinking about a reaction of 2 deuterons plus X, going to make helium-4, which is going to push off of X, and it's going to give us some kinetic energy in the helium-4, and we want to figure out what X is by measuring the helium-4 energy. Okay, so how do I measure the helium-4 energy? Well, if we had a silicon surface barrier, we could put it next to the electrode. I proposed this to my friend Mike McCoubrey, who's an electrochemist. Mike McCoubrey basically views the electrochemical cell as a cathedral. You know, this is where he lives. He lives in his electrochemical cell. And he's very picky about what goes into his electrochemical cell. And so he's gone to a lot of work to arrange the current densities to come in from all side uniform to maximize the loading as cathode to produce the excess heat. And he's saying, okay, you want to do what? You want to put what next to the cathode? I said, well, it's only a silicon surface barrier detector. I'm going to put it in. He says, well, how's your silicon surface barrier detector do for 1 molar lithium deuteroxide base? Probably not too good. And the question is if it's really close to the electrode to measure the alpha, because the alpha doesn't go very far, what's the current density going to be near the surface? What's the loading going to be? There's not going to be any loading there. So by putting the detector there, you kill the excess heat. So it's one of these arguments that trying to measure it, and if you're trying to measure it, it doesn't want to be measured somehow. So not so compatible with electrochemical cell. I could use a CR39 detector. People actually work with CR39 detectors, but they have the same argument that put the CR39 next to your cathode, that part's not going to be well loaded, so how do you get a measure? In general, it's not really an easy task to get a measurement of an alpha. So, fantastic idea. We'd really like to know the alpha energy. We're going to have to come up with some better approach to measure it. Are you ready?
Good question. CR39, is that a plastic kind of a thing?
Yeah.
It leaves a track? Is that the
Yeah,
idea?
exactly.
Thank you.
Okay, here's the brainstorm. If you can't put a detector next to the cathode, why not turn your cathode into the detector? Okay, so the idea is that I want to look at the palladium deuteride as a nuclear detector. So the idea is that the alpha is going to come in. When alpha comes in, it can hit the palladium, it can hit the deuterium. Now, if it comes in with enough energy and hits a deuteron, it's going to shatter the deuteron. And if, by shattering the deuteron, it's going to have a neutron come out and can detect the neutron out of the cell. Alternatively, you can have the alpha come in, and if it hits a deuteron, maybe it bashes into the deuteron, maybe the deuteron starts moving. If this deuteron hits this deuteron, or any other deuteron, if it fuses, because the cross-section's pretty good cross-section even without too much energy, then you're going to get a DD fusion neutron, which is going to leave the cell, which you can measure. So it turns out that our cathode is a superb detector of the alpha energy. All you need to do is calibrate it. So think of the palladium deuteride, or D2O for that matter, as your detector, and look for neutrons. So for the calibration, it turns out calibration is basically a standard problem. For example, at this point there's a Ziegler's trim code, SRIM 2008 I used for calculating range and energy deposition in palladium and palladium deuteride. The two curves are palladium and palladium deuteride. In the range, the alpha energy, this is, this is energy loss. So this is an MeV, 100,000 volts. This is energy, electron volts per angstrom. So 60 electron volts per angstrom to 20 electron volts per angstrom. So a lot of energy loss. So you can use that to figure out the range. So here's the alpha energy, and here's how far it goes. So for example, if you've got an MeV alpha in palladium deuteride, it's going to go 2 microns, less than 2 microns. So we can do it for palladium deuteride and D2O. If we know the range, we know the energy, we know the cross sections, we can start calculating yields. So here's the yield for an alpha breaking up a deuteron, giving a proton and neutron. So in palladium deuteride, basically if you're around 8 MeV or above, that's extremely efficient. you're going to shatter deuterons right and left. You can get neutrons coming out. You can measure the neutrons. And you're going to know that your alpha particle has 8 MeV or more. It turns out that the knock-on thing, having an alpha hit a deuteron, having a deuteron hit another deuteron, that's exquisitely sensitive. So here's the yield in terms of neutrons per joules of energy of alpha particles as a function of the alpha energy. So at 10 keV, 20 keV, 30 keV, namely, we have the possibility of using this new super duper Acme palladium deuterite detector of measuring the alpha energy down below 10 keV. Good detector, huh? So now we got to go to experiment. We need an experiment where excess heat was measured and neutrons were measured at the same time. So here's one example of an experiment where this is done. This is done in Japan, Takahashi and his team. And here's excess power on this axis. These numbers, this is 0, 50 watts, 100 watts, 150 watts. Probably you can't see it. This is an excess heat burst up at close to 100 watts. This is one well over 100 watts. Here's neutrons being observed. And I don't know if you can tell, but basically when the excess heat goes up, the neutrons aren't really doing anything special. Maybe there's a weak correlation, maybe there's no correlation whatsoever. And this is one of about a dozen experiments where neutrons are measured during heat bursts that's in the literature. And from this, my basic conclusion is that there's basically no correlation between neutron emission and excess heat. However, if I say no correlation, I can go back to the experimental data, I can quantify that. And the no correlation means an upper limit of basically 1 neutron for every 100 joules of energy produced. So there's not very many neutrons coming out, and the data is consistent with no neutrons at all. So I can use that to go back to my palladium deuterite detector, which I've put in so much effort calibrating by theoretical approach. So the 3 lines, calibration lines here, this is assuming no screening. This assumes screening consistent with low energy beam experiments. And this assumes screening at a level that's higher than the highest outlier from low energy beam experiments. So screening energy of 0 volts, I think this might be 400, I think this might be 800. We'll talk about that later another day. So Takahashi's data is consistent with this. Scott's here, Wolf's here, Gottze's here. And here's 1 neutron every 100 joules. And if I look at that, you know, the best numbers here, this would be 8 keV. So we basically know that the alpha, that when the helium-4 is born as an alpha, it's got an energy conservatively less than 20 keV, and from this argument perhaps less than 10 keV. Now, if the Q value is 24 MeV, and the helium-4 energy is less than 1,000th of the Q value, you can go back. This definitely teaches us something about the reaction. And what it teaches us is that it's not pushing off of palladium, as a very famous theorist pounded the table and yelled at us and said that was what was going on. That's inconsistent with experiment. It's not pushing off of a deuteron. It's not pushing off of electron. In fact, it's not, there is no solution. We're not dealing with a reaction that has a simple Rutherford picture. Basically, if you go to something that's heavy, like palladium, then the helium-4 would come off, the alpha particle would come off with 23 MeV. If it came off with 23 MeV, we get deuteron breakup, and we get neutrons at a level of 10 orders of magnitude more than is observed in experiment. If we get 2 deuterons pushing off of a deuteron, well, in this argument, this would give us near 8 MeV helium-4, which would give us deuteron breakup. also give us primary deuterons that are moving pretty fast, which would give us direct diffusion reactions level 10 orders of magnitude more than experiment. If we push off an electron, turns out the helium-4 is still going to have 76 kilovolts, which is ruled out by the neutron emission. Plus, we would get commensurate 24 MeV electrons, which would be a very exciting sight. So that's not happening either. Basically, there is no Rutherford D plus D plus X reaction that can be consistent with the observations. So usually when I do PowerPoint, I have Rutherford smiling, and then when we come to our conclusion, he gets X'd out, not smiling.
How many kiloelectron volts would be required?
How many keV required to do what?
To be consistent.
Conservatively under 20 keV, but strictly speaking, you'd probably be better be under 6 or 7 keV. Mind you, this is the same number that you get from tritium measurements. Tritium production was measured with neutron observations by collaboration between Kevin Wolf and Tom Claytor, and the absence of DT fusion neutrons was consistent with the tritium being born with an energy less than about 10 keV. So takeaway message. The goal was to learn something about the reaction mechanism by determining alpha energy. Proposed to use palladium deuteride as a detector, incredibly sensitive detector. Got the neutron yield for different alpha energies, data under 20 keV, no possible Rutherford picture reaction. That's my takeaway message. So I get to breathe. Comments or questions?
Neutrons can be detected. That is, if too low, maybe does not proceed.
Again, the neutron, it's sort of easy to detect neutrons if you got the right equipment. And the right equipment was next to cells that were seen to be producing excess heat. Basically, there's no neutrons there. And what that means is that whatever it is that's going on microscopically isn't like any reaction we've ever seen before. The final product, helium, is born without any significant fraction of the reaction energy, which is unanticipated. Okay, I've gone on too long. Mitchell's looking at me. Let's take our 10-plus minute break. We'll reconvene for Mitchell at the end.
Okay. A couple of things before I go through the review. One, I want to thank you all for coming. The only chance we have for this field succeeding is the fact that you're all here and have an interest. And Peter and I are sitting watching our colleagues die at about 3 or 4 per year. And if it wasn't for you people, I think you're the reason we're actually keeping going. I mean, maybe in the middle it was Mel, maybe it was, this discovery, that discovery, but it's getting really hard. The resources are really tough. So thanks for coming. That's one. 2, we inadvertently managed to pick up a couple of prime copies of Baudette's Excess Heat book. Totally sealed. If anybody wants a copy, talk to Gail after the course, okay? Also, she has a sign-up sheet on the colloquium if you want to get on that list as well. Any questions? Okay. I'm going to be showing today half of our work with the nanors and the nanomaterials. And basically, to review, the first day we talked about the materials in cold fusion, palladium and nickel, and the use of gold and platinum as the anode, because they would have a minimal amount of corrosion, a minimal amount of contamination on the active surface. But the problem I had is each of those cells that we showed had about $3,500 just of electrodes going in. So we had to find a way, 1, of cutting down the costs. 2, there was a lot of interest in moving from a large aqueous system to something dry. And so that was the dream, and that's what we're going to talk about. And we've been doing this at a company called Nanortech. And Gail Werner, Jeff Tollison, Steve Alaski are here if any of you want to talk to anybody about what's going on. So So today is dry nanomaterials. And basically, I'm going to talk about today, the first ones we did where we discovered electrical avalanches, then where we got near reproducible excess heat, very low level. That's how the standard nanomaterials deliver excess energy now. We actually went for a ride to the Weston Library, and I had this idea, and I said, Gail, we gotta go home and test this out. And to my astonishment, it worked beyond our wildest dreams. I'll show you with Series 5. This is where we were getting all of a sudden excess energy gain of 7 to 12. And by the time we got to Series 6, we were getting energy gains of 12 to 20, and that's why we took it to the course. I figure this is just too good to just keep discovering stuff. So we did, on January 2012, a open demo outside Peter's office, which we ran for about 4.5 months. Then we took the device to 2 other locations and did a number of other experiments on imaging and emission, which we'll talk about tomorrow. And Friday, we'll talk about the Series 7 nanors, and we're building the Series 8 right now. So I haven't had the luck of some people in the field where they build systems and they work right away. A lot of our stuff doesn't work. And we've gone down a lot of directions where there was low-level heat, things we couldn't control well. So it looks as if we had a direct line to the wind, but I assure you there were a lot of side directions. And we'll show you some of them now. And we use a number of nanostructured materials. The one that you're most going to be familiar with is the Zirconium Oxide. These are nanomaterials that have a ternary alloy. Think of a chocolate chip cookie, where the chocolate chips are palladium and nickel and deuterium, or nickel and protium. And the cookie itself is zirconium oxide, which is an insulator. So that prevents the sintering, it prevents aggregation, and it acts like an insulator. We'll talk more about it in a second. Again, the definition of nanors is we make these devices that look like an ordinary resistor. I'll show you some where we made them into transistors. But by putting in a DC current and being able to really control it, otherwise we get things that don't work, we're able to get energy gain. And we can run them in the DC mode for quite a while. And to determine semi-quantitatively how much heat energy we're getting out, we compare them to an ohmic controller. There are a lot of people involved in this. Most of them do not work in it anymore. Some of them don't work in it anymore. But it's been a lot of paths to figure out how to get to nanors. It was not a direct thing. We set up the company July 1st, and so here we are 6 months later. We've made 7 series of devices. Not enough to distribute to everybody in the room. It's a very, very slow production rate right now, but we're getting better. And our goal, of course, is to make clean water, efficient heaters. My goal was to try and make something where we have a platform. If we could have a platform, I mean, think back to the cat whisker. Who knew that the cat whisker would give us computers and internet, right? So, but put in the hands of creative people, that's what we got, and that's what we need here. Now, the reason that I really like the nanors is the same reason I like all cold fusion, which is when we look at energy density and power density, which is how many watts, or in this case microwatts, we get out per volume, we're way out here. And these are the typical energy production devices we rely on now, and we have a great, I think Rossi's device is over here. Dave Nagel just did a paper where he reviewed this in Infinite Energy. So all cold fusion systems are out there. I tend not to believe anything unless I do the experiment probably 20 times. I got into cold fusion to disprove it. That didn't work out too well. And now, actually, when we get results, I'll actually do a lot of work trying to disprove it. We'll set things up. We try really hard to not be fooled by false positives. So we do the verification we talked about on day 1, where we have multiple systems to measure the amount of energy production, both in parallel, for example, by measuring delta T, by doing calorimetry, by doing heat flow measurements, and in series, by looking at delta T, by making electricity, and by driving an engine. And so we have a series of corroboratory measurements that are semi-quantitative that really show excess heat. Okay, nanomaterials. If we put palladium in solution, we get a chelate. There's all kinds of palladium nanomaterials we've started looking at. Some of them form dendrimers, which are really gorgeous structures up to 200 nanometers. We can make them, you can go through all of this. There's quite a number of palladium materials that are being looked at or we're looking at now.
So it's 5 nanometer.
Oh, size is really important. We'll talk a little bit about that. It is believed that you get increased activity for certain small sizes, say something like 17 angstroms to 120 angstroms. Nobody really knows exactly what it is, but it's believed, in fact, that a lot of biological organelles within the mitochondria work for the same reason, that you get delocalized energy with certain size. So when we make these materials, as I show you, we actually try to make them as small as we can, and we have flammability limits. There's a whole other issue that we can get into. Okay, so we also make the nanomaterials with co-deposition structures. Palladium black is often used. Arata did that with Zan. We use these Zirconium Oxide. These are ZrO2 materials. A number of people have used them. And now what we do is we take a number of these nanomaterials and we preload them. And it's been really interesting learning how to do that because it's just not easy. And these are the materials before loading. Here we have, for example, nanomaterials. When you make the Zirconium Oxide material, it comes in as ZR in the metals. It looks like Christmas foil on Christmas trees. Comes in a bottle that looks just like either that or cut up aluminum foil, but very, very thin. And after we oxidize it, it looks like crushed bituminous coal. So that's what we have here. And then what we do, sorry about that. Then what we do is we load this material over weeks and weeks. Very tiny amounts of energy go in. The one that we showed at MIT, we only put in 70 joules to do the loading, but it was over a long period of time. So when we get excess energies of hundreds of joules and thousands of joules, we're not dealing with just storage. We're actually making a new material and then driving it in the cold fusion mode. Okay, so what are these materials? They tend to have zirconium. They're about 2/3 zirconium. This is before we oxidize them. We put in palladium. Some of them actually, we look with both palladium and nickel. And on Friday, I'll show you the result, the new devices we make with only nickel. And I'll show you some of the reasons why I'm moving back to palladium on Friday. Any questions?
I don't have the exact number right now with me, but this zirconium looks, the percentage is a lot higher than Arata's, right? Looks like.
I think you'll find it's very close. This is before oxidation. So this will drop down.
Okay.
As you begin oxidizing, this will come way down. I can show you, let me jump ahead. Yeah. It turns out they're very similar until we load them. When we do hyperloading, we change it, but it's a small ratio because it's D or H.
I was wondering how good the helium, zirconium dioxide was at dissipating helium
It's a good question. You got a good student there. You'll do well on the test. One of the interesting things in palladium metal is Peter was pointing out the different occupancy sites. It turns out there's a lot of them in the nanomaterials. Many palladium nanomaterials are characterized by a vacancy to begin with. And what we find is we're getting loading calculated of 300% or more compared to the palladium. And some of the ones we do are even higher. Now, I think what that means is we're either losing some of the D to the air when we're loading, or we're going to very shallow traps, and it's not clear that should be counted. But I do want to point out that these do have high loadings and probably a great heterogeneity of sites. All right. So we built the first ones. And this is actually out of order. Let me come back to that. Size matters. We want them as small as possible, but yeah.
Oh, sorry.
No, please.
I also found that one who is with Arata recently published the paper was zeolite, which is 0.8 with 0.8 nanometer palladium, and that's very small. But I wonder if zeolite will also work as a cookie dough.
I think we ought to find out.
Well, NRL put in a lot of work on that. Kidwell at NRL studied that for many years and has given presentations on it.
Zeolite, okay.
Still should try it. He didn't get a positive result, right? Probably, we can try it again. The problem with nanomaterials is, although palladium is well tolerated in the body, as is gold, nickel is not. So we were very concerned with the nickel impacts. In medicine, nickel is a real bad actor. All kinds of skin allergies come from nickel. And so the goal was to try and maintain it. That's where the origin of the nanors come from. The correct way to talk about these are called nanor type cold fusion devices. It really isn't supposed to be the name for the object. They're types of devices. Okay, and why do we like them?
It's become the name of the object, independent of what you wanted to happen.
So this failed.
You
I'm not
developed
doing
the
good with
nanor.
movies. All right, well, good things come in small sizes. You all saw the movie Prometheus, right? You didn't see the movie Prometheus? Yeah, I just got to get out more. Okay.
It wasn't that good.
Here are the nanors. Thank you for putting it up on the internet. And I'm not sure they look like firecrackers, but they look more like resistors. And so we either have them in the typical resistor combination like an I, or we flip them around like a U, so we can put them in a device. And as I'll show you on tomorrow, we've actually imaged these devices on CI39. So we took one of these devices, not actually a nanor, but an M nanor type cold fusion device. M is where we treat them with a magnetic field. We'll talk about that tomorrow. And it increases the output. And so we put one of the nanors over here. We can't see the wires. This is out of my lab notebook. And what we did is we laid a CI39 chip over it. I put one in my lab notebook, one elsewhere in the room, and then because I like to do things sort of blind, I sent them to Pam Boss on the other coast to etch. What you do is etch them in 5 normal sodium hydroxide for a few hours, and wherever a high energy penetrating particle or radiation goes through, you get a pit after you put it in the sodium hydroxide. And we actually imaged the device, and this is where it was right over here. So we actually are seeing very low level output from these devices. Here is the first ones we made. They have resistivities of about 4 megohm centimeter. And the reason I like them is I've switched to copper electrodes, which saves a lot of money. But not, this is expensive, but obviously this is a lot cheaper. We've made a number of these devices. These were type 2, where we put the probes in. We don't do that anymore. What we try to do now is, here's the active device in here. This is the cathode, this is the anode. I usually put a gold on for the anode. And here, for example, what we'll do is, here we have a ohmic, here's the nanor, here's an ohmic resistor, and then we'll put a big thermal mass around here. We'll wrap around either a container with water, boron nitride, or some other materials that we're looking at. So we'll put a big thermal mass on here, and then we'll put the temperature probes right next to it. So at the very center of the core, we're able to easily measure the temperature. And as I showed you, we'll put multiple probes on the outside, and we can watch the heat leaving. 2D and 3D nanor. Not all nanors that we use were in one dimension, where we just have the current going through the device. Here, for example, we use ultrasonic irradiation. We've been working with these nanomaterials for about 4 or 5 years now. So we do ultrasonic irradiation. We'll put a magnetic field through. Here, what we do is overloading with a second electric field, driving in more D. We've tried all kinds of things. This was the transistor. So here we have primary drive here and a spillover effect. we can go into this later. Basically, what's interesting is there's two optimal operating point manifolds. One was over here and one for here. We learned a lot. Very complicated process. This is the Series 6 nanors. What we try to do now, I showed you a number of nanomaterials. And we do a lot of processing. The reason we did this slide was, in the US Patent Office, if you file a patent in cold fusion, an application, usually about a year and a half, you hear, forget about it. They don't say forget about it the first week, they say about it. Forget about it later as they pull you in. What happened was when we filed this one, I think we filed it like June 1st. Within 2.5 weeks, we got a notice not to discuss it outside the US. It's since been retracted, which is why we're talking. But it did catch their interest. Before then, they said it didn't exist again. We have a lot of material for a field that doesn't exist. Here, as we make the Series 6 nanors, the interesting thing is here's the resistance, here's our calculated loading. We're getting incredibly high loadings with these. And as I said, because of the heterogeneity of sites, I don't believe it's all going into the material. But this is the calculation, and here is our peak. Okay, let's go to the next one. Questions?
Yeah.
Please.
Was that a resistance ratio
Yeah.
measurement?
That was, yeah. Well, that was a
The
direct.
black line, right?
It's not
It's the
resistance rate. You
but it
could
goes
get
up
the
by a
resistance
factor.
ratio.
So it goes up and then over there.
Yes.
So you're getting high loading over there. So you can actually use that for your nanners.
Yes.
Cool.
Okay.
Yeah, as a reference, the resistance was 4 mega ohms per centimeter.
Yes. Very high.
So it's a very, the active piece is extremely short.
It is very short. Our big problem with these, as I'll show you now, is very high resistances that go through avalanche. Some of these devices will have impedances of gigohms or more. I mean, we've gone as high as, I think, 10 teraohms or something. And suddenly, as I'll show you, it'll drop to 10 kiloohms. So if you have a kilovolt source on and you've had it all worked out, you suddenly hear a flash, your equipment's gone, you check your pulse.
Can we get an estimate for the resistance ratio at the high loading?
It looked like two, sure. They're right back
No,
there.
I mean at high loading. So how far down did it go?
I'll give you the original data. You can work it out.
So there it is.
Yeah.
So it started at 0.5.
Right, went to 1.2.
It goes to about 0.57. And that looks like about the lowest endpoint resistance ratio that I think I've ever seen, period. That is impressive. If it can be interpreted as a normal
Right,
resistance
right.
ratio.
But there may be other things going on with these materials.
I have a question.
Yes.
Why would you use a voltage source as opposed to a current source?
Oh, you're good. I'm done talking to you.
I mean, are you serious or what?
I am serious. I think it turns out that we have a number of things we do we think that is working. And one of them is control current sources. And we've been doing this since 80. Theoretically, it shouldn't make a difference, right? Bevan and Norton, what's the difference? But it does seem to make a difference, so we could talk about that later. Darn good question. Okay, so we talked about nanomaterials. Let's talk about their response to applied electric field intensity. So we wanted to know, do they have excess heat properties? Are there other effects? For example, as I showed you with the aqueous systems, when we get peak excess heat out, they put out near infrared. Do we see them with these materials? And then I was also interested, what's the impact of an applied magnetic or ultrasonic field on these? Just to summarize, we do get sometimes excess heat. We always get dissipation if we put current through, that's standard. But this is what kills us, is these unwanted avalanche breakdowns. And I'll show you those now. And the other question is, do we see OOP manifolds? We'll talk about that. So here's our setup. A lot of power supplies. And unlike, this is actually for the aqueous system, this is to remember, when we put the calibration pulses in, we always measure the currents. We have two separate circuits. And this is as before. We use multiple ways of measuring for heat output. Parallel diagnostics, we're looking at delta T. We divide by the input power. We'll show you why in a little bit. The heat flow, that's a secondary corroborating measurement. And then we do these other things. So we're putting in, by the way, with the nanomaterials, you can use a voltage source, okay? We use the current source mainly with the aqueous system. We do use voltage sources with these because the impedance is so high, it's essentially a Norton equivalent on its own. Anyway, so we're measuring the voltage across, the current through, the product gives us the input power in watts. And as I showed you, we can do the calorimetry. This was what we showed at the demo in 2012. The devices were in here, and then we could put a magnetic source on top. Again, as with the aqueous systems, we define input power the standard way rather than subtracting the thermoneutral potential. These are our definitions. We talked about this before. We don't have to do this again. The interesting thing is the drive circuits. We spend a lot of time controlling these devices. That seems to be key. In the aqueous systems, we had a driver, which really helped. I mean, I tried to get the community interested in it. They weren't that interested, and I just kept discovering stuff. Because the equipment opens up the ability to see terrain. I've told people before, it's like having the Louisiana Purchase in front of you. It's just all this turf. Anywhere you go, you just keep discovering stuff. Okay, so what we're going to do, these are our multiple ways of measuring. We use a control driver. We'll get into that later. Let's talk about the avalanche. So here we see a nanor within here. We're going to put the current through here. This is 4-terminal conductivity measurements that we do. And we do the experiment. We put on an applied potential here from 0 to 25 volts. We get an impedance that starts at 3.5 megohms, drops to 3 megohms. I went into the experiment over and over. I told you I don't believe anything until I do it too many times, and then this happened. Okay, this time it didn't keep going. We get a sudden fall off. So here we drop from 3 megohms down to 0.5 megohm, and we learned that we could even go more in terms of this avalanche, and we would always see it. So here, for example, we're increasing the electric potential. Here's a log scale, 10 volts, 100 volts. All of a sudden, the impedance comes flying down, and the power dissipation through it goes way up. It turns out that it's reversible. There's a little bit of hysteresis. We can take this device, we can increase the voltage, go here, we pass the avalanche. We're in this region where we're down to 4 kiloohms, so we can come back. It's a reversible process. So the question is there any excess heat? Well, in the beginning, when we did the Series 1, we didn't get any excess heat. It just did not work out. We kept getting the avalanches, and I was not impressed. But we didn't give up, and here's what we found. Any questions while we're doing this?
So when it drops, it's actually got negative resistance, right? Charge that you showed.
I don't think that's a negative resistance. I think it's a decrease.
No, but I mean, the slope, you're increasing the voltage, but the slope of that curve is negative, right, at that drop, is it not?
The slope of the change in resistance to voltage is negative.
Yeah.
DRDV.
Yeah, so that's a negative resistance normally.
Negative incremental resistance, maybe?
Well, there are some devices in electrical, in electronics that have a thing called a negative resistance curve. Normally, if you plot, V versus I, you get a straight line.
This
and
is
the
more
slope
like
is positive.
More like a diode or Zener diode, but there's no negative resistance or even negative incremental resistance here.
Okay.
The change at where, at which flow rate is the current? There is a sudden change in resistance.
You plotted this voltage, but you didn't plot current. You must know what current.
Oh, well, we could see that with the power. It goes way up, the current goes way up, because the power goes way up. Once you have the avalanche and the fall off of voltage, I can go back to the other one, you could work out the current, it goes way up.
But
That's why we lose the equipment.
the avalanche is occurring at what?
Voltage,
Yeah.
it's anywhere between 30 volts and 600 volts is where we see the breakdowns. It depends on the setup, it's prehistory, how we treated it, what the material is, what the configuration aspect ratios are.
It's related more on voltage than on current.
The way I arrange the experiment, it looks like voltage, but I'd have to think about that. I think it's it's the way I arrange the experiment with voltage. I'd have to think about it. We ought to go back and look at it, or maybe it's something for you to do. Series 3 nanors. These were a little bit more advanced, a new material. For example, here what we were looking at was zirconium oxide with nickel without palladium. And so we were putting on protium. And here's the control. Here's our input to the control. Here's our output to the control for power. Timer's down here. Here's our input to the nanor. Here's our output from the nanor. And when we look at energy, here's our input to the control, the output. They're linear, they're parallel. And here what we always see with excess energy coming out, we see a change, a superlinear rise. Not a lot to write home about, but it was better than seeing what we saw before. For example, here, we found out that when we drove past the avalanche, we lost the excess heat. This is really big, because now we know how to lose the excess heat, which does two things. It tells us that we really had excess heat. If we take a device and we bring it back to the equivalence of a resistor, that shows our calibration was right. Two, it shows us regions to avoid. So for example, here we're seeing the input to the control. All of these are the same, except some of them are going to have calibrations. And here's the input to the nanor. Here's our output from the control. And look, we're getting less out than in. In region 3, after the breakdown, we lose the excess heat. This is very big in terms of a discovery. So here, we get the match. Here's our input, there's our output. Questions? Okay, the other thing that we found was Bob Bass, who's a great theoretician in cold fusion, had been suggesting his 5-needle paradigm to prove cold fusion. And 5 needles means you look at 5 input powers of increasing input and see if the output goes up linearly too. So we finally did the experiment for him, and here it was. And it was nice because we have a system with the Series 3 nanor, not a lot of excess energy out, but controllable. So we can put in ohma control, cold fusion device, ohma control, cold fusion device, ohma control, and we're able to show the increase in output or decrease as a function of how the drive is. Questions?
So, Mitchell.
Yeah.
So in essence, what I was impressed by for your nanor is you turn the current on, the nanor produces excess heat. You turn the current off, the nanor stops. So your excess heat events here are where you turn the current on through the nanor.
Correct.
Turn it on to produce these needles.
Correct. And by the way, this is the temperature, so we're going up roughly, well, here's 26 degrees, 19 degrees. If we take the delta T and divide by the input power, this is what we get. And that's really nice. So here's our controls. And here is the cold fusion device. And the ratios, the reason I like to do input power normalized is the ratios gives us our excess energy gain. Better? So the energy gain is this to this, this to this, this to this. We've actually done an experiment now where we've done 5 input powers and found the response. Here's some more of these. This is the calorimetry for that experiment. So here we're actually looking at power, input and output, and the energy over there in joules. And here's yet another one where we're oh, this is interesting. We're very interested in looking at materials that destroy the excess heat reaction. Seems stupid because we're also looking for things to increase it. But we do have to look, and some of them actually shut it off. So here, for example, we added silver doping and drove it to zero. I mean, we just drove the excess heat to zero. To me, it's interesting because, again, it shows the calibration was right. So what did we learn from Series 3 nanors? That we could get low-level energy gain from dry materials, that we had to drive them before the avalanche and as close to the avalanche as possible, and that there was, in fact, the appearance of the first optimal operating point manifold for the nanomaterials. Any question?
What's the time response when you, the excess power when we shut it off?
Excess power when we shut it off. Let's look at one. Okay, apparently we're still getting heat out here afterwards. Here's the input. And so there's a little lag coming up, and the difference is, I apologize for how I measure time in these. It says 2-second intervals rather than the absolute time. As we run the experiments, some of the experiments are very long. We change it in a sketch. That has to do with software that came out of the Media Lab. So when I change it, I'm able to change the time of the interval. And so I apologize for that. So the answer here is this would be the difference for the fall off.
And what about the time on the cascade?
Pardon?
What the response when it
Okay. Okay, this was working pretty well. We felt now we knew where we were going to get excess energy, hopefully. So we made a new series, the Series 5. And this is where we first did preloading. And this is the first time we started getting significant excess heat in the dry materials. All right, so here's one. This was the second one we built of this series. These are the control pulses. Each count is 7 seconds. If you can't read it again, I apologize. These aren't the time in minutes. Each of these is 7 seconds. Here's our input to the control. Here's our output from the control. Now this is input power. This is delta T normalized to input power. So if it wasn't normalized, you'd see this for the output. But by normalizing it, you get a number that's flat, roughly. So the energy gain is going to be the ratio of this to this. Here's the input to the control, the output. Here's the input to the nanor, here's the output. And by taking the ratio of the output, delta T, to the input power, it becomes a constant. It's not really a constant, but compared to the other way of doing it, it is a constant. And so we can take a ratio and get the energy gain. Questions? Okay, let's go to another one. I told you I like to look at multiple ways to determine we have excess heat. So looking at delta T, it clearly was excess heat. But in addition, what we do is we measure the heat flow as it leaves the calorimeter. So here, for example, is the heat flow. Here's the input to the control. Here's the output of the heat flow. Here's the input to the nanor. Here's the outflow through the same heat flow. Remember, these are right next to each other. I showed you the pictures. And then we repeat it. Here's our calibration pulses and the ohmic control and nanor. And so here, by heat flow, this is our energy gain. So now we have energy gain both by delta T, one energy gain by heat flow, and here's our calorimetry. And this also shows heat flow. So usually in my notebook I put a little smiley because I'm finally happy. We like to see 3 simultaneous systems showing excess energy before we believe it. So here's our input to the control. Here's our output. Here's our input to the nanor. Here's our output. Here's the calibration pulse. And you can't see the first calibration pulse. And here are the energies. And again, these are it's a superlinear rise because we're having increasing input, but these are matched as opposed to here where we're seeing energy gain. Questions?
So that's the input power.
The blue is the input.
Yes.
What we're doing is we're taking the power supply and putting it first to the control, then to the nanor, then to the control, then to the nanor.
So the control is just a resistor.
Yes, yes.
Isn't that ratio will hold even when the power is higher? Like when the power is 100 watts?
We're going to show you. No,
Okay.
you're moving ahead. You guys are too fast. All right, let's look at the electrical resistance as a function of time. This is why we have trouble with nanors initially. See, here's our aroma control, well behaved for a resistor, isn't it? What would you expect? But the nanor is not well behaved in terms of electrical resistance. It's very difficult to control because we're getting a fall off with time. And this, as I say, this can be, I think this can be up to 7 or 8 orders of magnitude suddenly.
What are the units?
These are probably kiloohms, I think. I think we're talking kiloohms. I should have marked it. Yeah, that would make sense because this is about 150 kiloohms. All right, so we built another one, and I'm gonna just run through for the next 20, 30 minutes, 130 experiments, probably more data than you've seen from too much else. But the object is to get your eyes to see when there's excess heat and when there isn't. Okay, so we're going to show the same kind of graphs all along. Here's our aroma control. Here's the temperature rise. Here's the nanor, the core temperatures. Yike. All right, here's our heat flow. Here's to the aroma control. Here's to the nanor. So we're putting less into the nanor, and look at all that heat coming out. Okay, let's look at more. This is the same run. I'll tell you how to read these. This run was, the experiment was done January 3rd, run B. What we do, because as I told you, with the nanors, we can do multiple experiments a day. So the first one's A, and some of them go up to Z, and then we start again. Not too often. But B is the second run of the day. And so here is our calorimetry for nanor 503. Ohma control here, power in. Here's our output for delta T normalized input. And here, less in, higher temperature. This ratio is our energy gain. I'll show you some more. This was interesting. The calibration pulses we put on at the beginning to make sure our voltage and current measurements are accurate in the computer. Because, they're not exactly the number, but they're linear proportional to the number. We want to calibrate it. So that's what this was for. So we do a calibration to the ohma control. We do a calibration to the nanor, and here they're well behaved. We put in 1, we get the output current. We put in a voltage to the nanor, we get an output current. What you're going to see later is some of these are delayed, and we're trying to figure out why. But we'll talk about that later. Series 5.2. I don't really want to talk about this. Sometimes when we make the nanors, there's a sudden release of gas, and it'll burst through the side. So it's a manufacturing problem. See here's these calibration pulses. The ohma control, the current is synchronous to the applied voltage. But with some of the nanors that are very high power, we put on the voltage and the current's delayed. Well, there was the first one that we saw that. And I don't know what it means. I mean, I have guesses what it means, but it is interesting physics.
So that means that the power is increasing with time.
It means that there's a slow response of the material, and that it may have ferroelectric properties where you end up getting an induced polarization that lasts beyond your applied electric field intensity. I think that's what it means, is an induced ferroelectric component. But I don't know. I'll find out. Okay, here, this is just more of the, it's just going to be the same thing over and over. We're going to go through a lot of them where we look at delta T. Ratio is the excess energy gain. Notice this falls down a bit as we increase the input.
Yeah, so Mitchell, your axes for your power, the input power in this case might be the green. So that's 15 milliwatts or so.
Right.
Would you like to comment at all about this being a small, low-power device?
Okay, yeah. I built these to come to the demo in Peter's lab. And what a lot of people don't know is that when we did the aqueous demo in 2003, we had hundreds of people in the room in the afternoon. And somebody disconnected the cathode and put it on the chair. And as a result, I've never really trusted leaving anything alone since that day. So I wanted to make it low power so we could run, so it wouldn't be a problem. And so we made this to operate at under a watt, actually around 100 milliwatts. But they don't all have to operate at that. That was designed to be this way. Is that what you were talking about?
I was saying your turnaround time for the experiments are pretty
Yeah,
quick
too.
with this as well.
That too.
You've made a lot of progress with these nanometers. But they're very small, so the low power is appropriate. So high power density goes to low power.
The active material in the nanors ranges between about 20 milligrams and 100 milligrams at the most. The one that was in your office is 35 milligrams.
Sometimes your highest excess heat or delta T is at your lowest current input, and sometimes it's way further down the line.
Right.
Sometimes it's like this, and sometimes it's like,
That's right.
just, does it happen randomly, or?
I don't think it's random. I think it's a function of the material. And we'll talk more about that later. Good pickup. Here, for example, is, again, delta T normalized the input power. This is a run later. That's the energy gain. Here's another one where we're looking at the full calorimetry. So the energy gain is going to be, actually the energy gain here is this to this, is the power, power gain, and the energy gain is here. On calorimetry, you read just on the nanor, top to bottom, to get the gain. On all the others, you read one side to the other. We'll talk about it.
It means to keep constant the energy input, the power.
Yes.
You need to reduce the voltage because of the decrease of resistance.
That's right.
So
We do follow that.
dynamically adjusted to keep the power constant.
We don't necessarily keep it constant. We tend to, in exploration mode, we increase it over time. All right, here's some more. We're not getting back all of the heat we're putting into the ohmic controls, so we know the output of these are going to be actually a little higher. So the energy gain that we detect here is going to be a lower limit. And here too, we see these are matched, and here it's rising. This is the heat flow showing excess energy, ohmic control, cold fusion device, ohmic control, cold fusion device, yada, yada, yada. So again, we take the ratio to get the energy gain. Let's get that for now. Here's one where we take the ohmic control, we put on the applied voltage, we get a current out to calibrate, and look at this, we put it on the nanor and the current doesn't come out till later. That was a really well-performing device. And again, I don't know why this occurs. There's got to be a whole lot of material science here and metallurgy that we just do not understand yet. So please, one of you help me out. Give me a second here. Okay. Questions? All right, we'll go to the next one. I was so,
Do you
yeah.
want to say anything about what's different between Series 3, Series 5, Series 6?
Yeah, I'll do that now, sure. Series 1, we were just screwing around with and learned about the avalanches. It really took almost a year to learn how to put these into the excess energy region. That was the Series 3. Series 5, we started loading. You take the basic material and we found a way to increase the deuterium concentration inside it and let it stay. And we sort of screwing around in 5 and 6, we really nailed it. And that's what I'll show you here. At least I think we nailed it, because we did that demo, and when we walked the class to Peter's room, the energy gain was 14, and the last one I had done was 2.7 in that room, so I was happy as a clam. Okay, Series 6. What happened was, as a result of an idea I had in Series 5, we upped the energy gain from about 1.3 to 7. And I said, this has got to be the way to do it. So the difference in 6 is we kept it going. That's why we got the R over R zero curve to come up and down. And we went way longer than we did on the earlier ones. So these are hyperloaded. 5 were preloaded. Sorry about that. 6 were hyperloaded. We brought them to the demo, and we'll show you the results here.
Sorry, but when you say that it's partially preloaded, it means that you do loading with deuterium before.
Yes, or protium, or both, yes. Yes, we prepare the device. It's proprietary how we put it in and keep it in. But the nice thing is you can hold it, you can move it. I'll be able to show you results tomorrow where we looked at the impact of magnetic fields and imaging, because we could pick the device up and move it. And it's hard to do with the bigger devices. So here was our first Series 6. And it's very low level stuff for the first one. Okay, here it's getting a little better. Heat flow. We're learning a lot. Let me jump ahead here. Okay. By the time, this is just before the course. So here's our control pulses, because we want to calibrate our meters. Here's the input to the ohmic control. We're looking at full bore calorimetry. So this is input and output power. Oh no, I apologize. This is input power, and this is delta T. So the input power is here to the control. The input power is here to the nanor. And so for this input, we're getting this temperature. This input, we're getting that temperature.
What's temperature divided by power? Input power.
Yes. So this would be the ratio of the gain. So here you see we're seeing a big energy gain and a smaller one here, which is still greater than 1. Here's our raw power data. Let me jump ahead. We're getting closer. These devices tend to mature over time. When we first make them, for some reason you watch these curves, we don't get as much excess heat out. We've learned ways of improving them over time. So here, for example, we're looking at delta T and input power. Here's the ohmic control, delta T. Here's the delta T to the nanor. We're getting more out. Now we normalize it to input power. So here's the ohmic control, and this is our ratio. And the 20, I think that was the day I called you up. I said, Peter, I'm bringing it in. And we decided to bring it in because it was a great energy gain. And here's the calorimetry, input and output, input to the nanor, output, and look at that energy gain right there. And then we decided to do the demo at the meeting, and all of you wonderful people came and had that was the first class we did 2 years ago. And then we went back to the room and we had the following. To my delight, having left it alone during the class. Oh, that was the other thing. We built this device to run through a sequence in 2 hours so that it would fit Peter's class. And that's not necessarily the way you want to do an experiment. So you'll see later tomorrow when we talk about magnetic fields and other things, the first thing we did was widen it to 8 or 10 hours. Anyway, what we saw here when we went back at the course was a power gain, energy gain of around 13 by delta T. The heat flow detectors weren't working the first day. And by calorimetry, and we had a gain of 14. And here's the data. So here we're looking at delta T and input power. Here's the control. Here's the delta T. Here's to the nanor. There's the delta T. Less input power, more out. Now we take the delta T, divide by input power, and we get the energy gain by taking the ratio of these two. If we do calorimetry to get the energy gain, we take the ratio of this to this. Actually, I apologize. This is the power gain. The energy gain's here. So if you want to do the energy gain there, it would be there to there. Questions? Okay, we'll keep going. We kept running it. It turned out that we ran the device in Peter's office for about 4 months. And later that night, the heat flow device did turn on. So we were getting now, finally can draw the smiley, we get energy gain by delta T and by heat flow and by calorimetry. And here's some of the results. Here's delta T. This is a run after the course. Here's the delta T normalized. So here's our energy gain. Here's the heat flow. Here's our energy gain.
Decreasing over time.
Yes. What we do is I'm going to show you a series of sequences for between 2 and 8 hours, and each of them is repeatable, and that each gets energy gain. Yeah.
See, around the time that this was done, we got a lot of calls about the experiment. People were very curious. Some of our colleagues at NRL were very skeptical. I said, well, all that's going on is that zirconium is being oxidized, that he's starting out with zirconium and completely oxidizing, and that's the basis of the energy. So I said, okay, let's calculate it. So I twisted Mitchell's arm to tell me the mass. I said, well, let's assume it's all zirconium. How much energy would be produced if you burned all of it through? And then we compared it against Mitchell's experiment. And Mitchell burned through the total chemical energy you get from zirconium burning in about a little bit less than an hour. And this thing ran for months.
Actually, a year. We'll show you the rest.
So do you have a data series over?
I'm about to show it to you. Sit back. Hand out the popcorn. I should have brought popcorn. You watch the days. What we'll do is we're going to move ahead day by day initially, then week by week, and finally we'll go over a year. And you'll see it's not all continuous. You'll see. So here's our delta T. Again, because we didn't divide by input power, we don't have a flat line. And you can't take ratios to two slopes. So we take the delta T. Now we can get the ratio and get the energy gain. And we see energy gain with the heat flow too, and with the calorimetry. On it goes. I could go through them all, but
Mitchell, were you
Please.
ever reloading this?
No.
Was this just, you just loaded it at the beginning and
Correct.
then you ran it for a whole year?
Correct. Not with 100% duty cycle, but over the duration of a year. Probably the duty cycle was probably closer to 10%. When we were at MIT, I think we were running around 30-40%. But when I was taking it to other places, we were doing focal experiments. Okay, so by the 31st, we're still getting nice energy gains. I'll just run through them. You can see. As I told you, this is why we use normalization. Is if you don't use it, you can barely see anything, and if you normalize, it comes out nice and sweet. You can easily get the energy gain. Here we did experiments where we drive both the nanor and the resistor. It's a waste of time. Also, we like it now when there's big separation between the two. We'll show you that in a second. All right, Peter said, why don't we try a protocol where we go to the OMA control, we wait a long time, then we go to the Cold Fusion device, wait a long, makes sense. I mean, we had done that before, and the reason I put it together was to increase the duty cycle. So we did a little of these too. And so here's this is delta T in input power. OMA control is what we get out, put in less, get out more. Okay? And if we look at delta T normalized to input power, again, this becomes flat. We can take the ratio and get the energy gain. Heat flow, again, we get an energy gain, heat flow normalized to input power. And ba-bing, we got 3 in a row, so we get the smiley, we're happy, we got 3 proofs of verification of excess energy. And here we get the match of input to the OMA control. Here we get a massive increase of energy gain to the Cold Fusion device. Okay, things aren't always good in Mudville. It turns out that these materials can be destroyed. So this nanor actually had a burst of energy inside, and what they do is there's a little hole in the side that occurs, and the stuff squirts out. And here, when it's squirted out, it drops down to an ohmic control. We end up losing, for whatever reason, in that material, as a result of this catastrophic effect, we lose the excess energy. It goes down to a gain of 1. And so here too, even with the heat flow, it comes down to match here to here. So here's the excess heat, and then it comes down. Okay, here we take the cell, and this is before we did the magnetic experiment. I'm just showing you that in May, when we lose the excess energy, we can get it back over time and fix the hole. There are things we can do to bring the energy back. So here it is later. Not as much energy gain as in your office. It's deteriorated a bit, but we're still getting excess energy. And the reason we did this is in Natick is where we applied the magnetic fields, the high intensity. We did 1.5 Tesla, where we were flipping, we'll show you tomorrow, putting on 1.5 Tesla fields, flipping them every 10th of a millisecond, and putting on pulses that induce about 40,000 volts per meter across the device. That's how we make the M nanors. Anyway, here, before it becomes an M nanor, here's our energy gain. So we're still getting energy gain, and we see it for the heat flow, we see it for the calorimetry, nice energy gain. And here's in February, I think this is November, not February. November, we're still getting energy gain out. And here it is in November, the final run before we put it in the museum. When I run these things, eventually we store them because the day may come when we want to examine them closer. So this was actually the last run we did. Here's the input power to the ohmic control. Here's the output. Here's the input to the nanor. There's the output.
That last one looked like the gain was very high.
It wasn't. It's an M nanor. This is after we treat it.
Roughly, how much gain would that be?
It's a lot. It's a lot. We like M nanors. The only trouble is they have that cyclicity I don't like.
Kind of looks like over 50 to me.
It is. Yeah. The M nanors run as high as 80. And you saw cold powers will show on Friday. Sometimes it's higher. Anyway, the take-home point. We have a cold fusion device which is portable, which is dry, which is preloaded. Doesn't put out kilowatts yet. We need 80,000 watts per call, but we're working on it.
So Mitchell, this technology looks really interesting, and even though it's small scale, you know, if you made 100 nanors, you could put them together and have something that would do a little bit better. What would it take to get this commercialized sort of as is without doing this a lot more development?
We need somebody to help us make electronic components and to make electronic instrumentation. So if there's anybody in the room, come see us afterwards.
Just a quick question, did you ever run any tests at elevated temperature? Because I noticed that your delta T was about, what, 1.5 degrees or something like that?
No.
So you're basically at room temperature, right, for the whole system?
We have tried very hard with the pre-Series 7 to keep it locked at low temp. Because we wanted a fast rise time, fall time. We wanted safety. And frankly, since it was running at his lab alone overnight, I guess we did do that with the first one. But I was concerned that I wanted it low power, low temp, just so we could leave it going. Okay, so I think the important thing is it was 35 milligrams. That comes up to be about 19,000 watts per kilogram for our energy density, for our power density. And in fact, if you use the palladium rather than the zirconium, it comes up to be about 65 kilowatts per kilogram is what we're getting at. Questions?
Comment. In my view, the nanor is revolutionary. I mean, Mike McCoubrey had been interested in separating the loading from the excess power production for many years and succeeded in doing that in some cryogenic experiments, you know, earlier than the nanor stuff. The this is stunning in my view. It's a very important experiment.
Well, we could stop here, or I could show you some of the failures.
Stop here, I can make fingers.
Okay.
I was gonna ask you about that too. You said earlier you're gonna show us the difference between when you got real excess heat and when you didn't. And you kind of showed us a lot of examples where you did get excess heat, but I didn't see any where you didn't.
There's a lot where we don't. The real interesting ones are where we get excess energy and hurt the nanor and bring it down to the equivalent of a resistor. I mean, we were going to talk about one on Friday. I could show you quickly. Will I get in trouble if we jump ahead? I'm not supposed to do this till Friday. When we started doping nickel ordinary water systems with heavy water, we found that we damaged the nickel. And so we see increasing power as we raise ordinary water with more D2O, but we damage the nanor. And so here's our control, here's ordinary water, here's with 3.7% heavy water. And I don't know if you can see it, but that nickel is very different from that nickel. The resistivities are different.
This is fusers, not nanors.
Yeah, I'm sorry, fusers. Thank you. Thank you. But the point is that they damage, and so they come down below a resistor. I think that was the issue that I thought you were talking about. So here's a control, here's where we see the excess energy, and if we damage the device, it comes down equal to the control. And I also showed you the one for the nano.
How long can you maintain those two metals sitting on in the room? How long can that last out of the? And how long can they last? Don't they get oxidized?
They are oxidized.
Already.
We spend a long time oxidizing them. That's why they turn from looking like aluminum foil to crushed bituminous coal. They're totally oxidized.
And the D2 gas don't get out of the metal?
I think it does. I think on occasion it does. I think that's the biggest loss we have. I don't think we're burning up the deuterium in fusion because it's only 10 to the 11th we lose per joule. So I don't think we're burning that up. I think we do get lost to the environment.
But it can last for some many years, some years.
We haven't tested many years. We know we can do 1 year.
Doesn't have like a half-life for dissipation of like the.
Good question. We'll talk about that on Friday. Great question. No, if you look at these nanors that I showed you, the series 4 and 5, the peak gain falls over time. There is a fall off. And you'll see that changes with the application of the magnetic field.
Are the nanors sealed? Do you understand that? The nanors are sealed?
Hermetically sealed, yeah.
Yeah, and so what about helium production? Is that increase the pressure?
It's a good question. I mean, the materials right now that we make in the jacket are helium permeable.
Oh, okay, it leaks out.
It could, but we got to do that experiment where we take one of the nanors and put it in high helium and see if it shuts off. A lot of good experiments we need to
Measure
do.
the helium production.
Yeah, too. Yeah. Yeah, no, our problem is we're strapped for funds and don't want to whine about it, but that's what's stopping the research here. Okay, should we show you any more or we take a break for today? Pardon?
I can make egress.
Okay, so we'll see you tomorrow at 10:30.